يلا المفروض انه شغال الان. ابو محمد ابو محمد
هذا الميكروفون ما يكفي.
ما يكفي، ما يجي صوته كويس.
طيب هذاك واحد ميكروفون كافي صح؟ هو واحد ميكروفون بس.
ايه؟
واحد ميكروفون بس.
Do I present from here, standing here?
Yes.
Okay. Not there.
Here only.
Here for the microphone.
Yes. Yes.
Oh, that's good. Works for me.
هذا شوف برضه خليه هنا حق الزوم.
طيب بس عايزين نجرب اللابتوب بتاع الدكتور هيعرض من عنده.
بعد هذا مو
لا هو في الاخر عنده الدسكشن مع الدكتوره سميه.
طيب بعد الان بما انه ترتيب ما
عايز يجرب بس عايز يجرب.
المشكله لو يجرب الان
ممكن نفصل دي بس.
Sure.
جرب الصوت.
جرب الصوت.
دقيقه بس خلاص. شير سكرين ما اعرف كيف الطريقه في الزوم. بتاع الزوم هذا سلايد شير سكرين. سكرين كامله ولا سلايد؟
تبيها كامله؟
ما ادري. شاشه كامله شير يا
تطلعون بعد السلايدات في مكان في شيء تبي تسوونه؟
ما ادري. وين السلايد اللي شغاله؟ شو اكثر من واحده فاتحه؟
لا بص اول واحده على الديسكتوب مفيش غيرها.
هذه
الفيرست فين الفيرست؟
هذه فيرستين.
خلها على الشاشه كامله. لا تغيرون سلايدات بعدين تتحمل الثاني.
لا خلاص اليوم هذا هو اللي شغال.
بس افتح دي يا سلطان. افتح اللي هي الفيرست دي. اقفل دي عشان تتاكد. اقفل كله.
هذا بيقفل.
اقفل كله. اقفل كله عشان نمسح الباقي عشان ما نتلخبطش.
ما راضي يقفل.
هتعرض من الزوم.
ابى اخليه شير في الزوم.
قصه
ما نخلي الشاشه كامله. هذا
هي
بس
دي.
هذا اليوم شغلان اليوم.
ارجع شوف كلمه الدكتور عبد الله كام سلايد.
كيف
انزل بس 3 صفحات خلاص. هي دي اخر. افتح الثاني. امسح الثاني عشان ما حدش يغلط. من مايس امسح دي بس. هي دي
هذا رقم الزوم. هذا شوف هذا الاي دي حق الزوم لو واحد يحتاجه.
انت تبغى واقف هنا. نو واي.
المفروض انا بجوا الحين قصه شريطه بروح انا.
You want to just try Dr. Philip?
Yeah, sure.
طيب.
Can I just take this?
Justice. طيب. طيب.
شيل السلايدات.
دقيقه بس.
هو عنده
بس بيجرب.
دي خلاص بعد ما نخلص
Yeah, sure. You never know.
But is there a problem for if you present from your laptop? So stream live will not cover. We have here stream.
Okay.
Right? Up to you, yani.
So better
for stream live
from this laptop.
Yeah, but here I have all of the animations.
خلاص اوكي. يعني هو عنده اللابتوب عليها الانيميشن.
طيب ممكن نعطيه الصلاحيه هو يدخل اذا جاء يفتح المايك. صوت كشف مشكله.
صوتين.
Is there a way that I can go live from
Go live
here?
from here.
Not from here.
Yes, from here only.
The microphone is connected with this.
Yes, mic for stream live بس for mic.
لا بس هنا مايك ما راح يلقط لأن هنا مربوط بمايكات.
المايك also Dr. Philip المايك this mic.
I'm busy in the.
Right here also.
Sure. Okay. So let's see what we can do.
No way to.
Maybe.
Okay.
Send it.
No, not send it. It's 200 meg.
Okay.
I can try and save it.
PowerPoint presentation only or
Yes, PowerPoint.
The college. خلاص. In the college I didn't have. Okay. في HDMI extra.
Yes, Ahmed.
بالله شوف.
Hello.
أي شيء.
I'm in the not immediately. I'm in the conference and I need to save the file and transfer it. No, I cannot be there.
وين الشيء؟ هذا ليش؟ يلا شيف اذا فيه موجود. شغل تست الحين باقي كم؟
أوكي.
باقي 10 دقائق يجي هنا.
إذا الميكروفون تاخذ هذا يجي صوت سمع. أنا أسوي رقم ثاني.
انا ما تست. يلا. الو الو حياك.
embed phones. Okay.
تمام. طيب الريموت في الشنطة عندك بعد الظهر. في حدا شنطة؟ اي في شنطة اللابتوب. الا انا حطيته قبل شوي في شنطة اللابتوب. اي البوستر الفلاشة وين؟ طيب شوي بجيب لك الفلاشة. خلي واحد يجيبها بس يطلع منه ويجيبها. يلا يعطيك العافية.
الو
طيب كيف الحل الحين؟ ما عندنا وقت نجرب المايك.
هو هياخد البرزنتيشن هنا.
بياخذها هنا. قال بياخذها ولا؟
لا هيجي هنا خلاص. هنا
شوف انا بصلح هذا. شوف
عايز تجرب زوم؟ بتجرب زوم.
بس انا ما ودي اني تطلع الشاشة فيه عادي.
انا خايف من الزوم شير هنا. عايز اجربه بالبرزنتيشن بتاعي.
طب ليه هذا زوم؟
عايز اجرب بتاع ده. حضرتك بعيد.
طب يلا هذا شير.
يلا
ايه USB drive.
Yeah.
Which one?
Which
This one?
Yeah.
Okay. When you present, we need to share the Zoom.
So I sent the PDF. I will resend a new PDF because I changed two things, and the PowerPoint needs to be deleted. You cannot keep the PowerPoint. Okay?
After finish, يعني?
Yes.
No problem. Delete. After
Sure.
finish, delete.
Okay.
Your files. Don't worry.
Okay, good.
خلاص. I will close because
Yes.
after you finish, inshallah, I will open.
I just want to check if there are all of the okay, good. And you can close it.
Okay.
Thank you, sir.
You're welcome. عبد الله حياك.
جرب.
ايه
جرب اليوم.
طيب يلا هي بحاول اجيك. يلا يلا
ايه
خلاص.
حد جاي؟
مدير الجامعة
وصل هيجي هنا دلوقتي لسه المعرض صح؟
ايه معه.
لسه اعتقد صح؟
يا اخي انا ودي انه
جرب زوم. حسن انا فرضت اسمه صوت ولا مؤسف من سبيكر.
ايه هذا نبغى اجرب. يا سلطان وين سلطان؟ سلطان عتيبي.
اللي هيقول السلام الملكي.
شاطر شاطر. ايش؟ هلا حياك يا مرحبا. سامع الصوت عندنا؟ اي
بيقول
ودي ان احد يكون يجرب على
صح
طول.
ما يحتاج يطلع المايك.
الصوت
لا يطلع في المايك
وكويس حلو.
قول ابو
شايفين البرزنتيشن؟
3 كلمات.
تمام يلا تمام يلا. اي بنمشي على كده، ما في حل الا كذا. يلا
مش محتاج احد اول ما تظهر السلايده، اول ما تظهر السلايده يشتغل النشيد الوطني، خلاص الكل يقول.
لا احنا زي كذا خلاص تمام. حتى لو ما صار قريب يعني ما في حل الا كذا يعني، ما نقدر. اول حاجه يلا تمام.
خلاص كده يا عمر.
يلا يعطيك العافيه. يلا يلا. لا خلاص، وين هذا الميكروفون الثاني؟ وين الميكروفونات اللي هنا؟ كله جي كم مايك؟ بس اثنين جيب
فيه المايك حق الجيب.
الو وين هذا حق هنا؟ ركب هنا. بسم الله.
بسم الله بسم الله. ضعيف الصوت، ممكن ضعيف من هنا.
هذا كيف ها؟
ضعيف الصوت من هنا.
والله خلينا نكرر.
بسم الله بسم الله.
ما في حل الا كذا. شوف حاول
انت والحساسيه حقته شوي.
عندي والله اقدر. ما في حل الا كذا. في هذا شوف حط هذا شوف
هذا ممتاز. لا في حق هذا.
كيف طفي هذا مايك؟ اخر.
بسم الله. زين the sensitivity of this mic. Can you increase it?
Which one? This one?
Yes.
No, this one. Fix it. This should be good. Yes.
اي طيب خليه يصدق.
Okay, if you have. From the control.
No, not possible. These are not possible.
already high.
Full.
This.
No, full.
We have a stand.
شوف.
To handle.
ايه هذا المايك الثاني هنا، خلي مايك جاهز كله. بروح اشيك مع تيتر بس.
أقول ولا كان؟ مش محتاج. الصوت كويس.
الصوت هنا تعبان. الصوت هنا كويس. لكن المشكلة محتاجين ستاند عشان يبقى ثابت. بسم الله.
بسم الله بسم الله بسم الله
بسم الله الرحمن الرحيم.
This no place for the start. Right. There is no place for the start. Yeah, what this like this.
Yeah, I got it. I know. Put here.
Which we have already. Start.
I don't know now, guys. We need to search.
This is my course.
Yeah, I know.
Oops. صلي الله عليه. على نفس الحال. تمام. بس طيب.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين، ثم الصلاة على خاتم الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين، وبعد. معالي رئيس جامعة الإمام عبد الرحمن بن فيصل الأستاذ الدكتور عبد الله بن محمد الربيش، سعادة نائب رئيس الجامعة للبحث العلمي والابتكار الأستاذ الدكتور فهد الحربي، سعادة عميد كلية علوم الحاسب وتقنية المعلومات الدكتور عبد الله بن محمد المهيدب، أصحاب المعالي والسعادة، ضيوفنا الكرام من داخل المملكة وخارجها، السيدات والسادة الحضور، حفلنا الكريم، السلام عليكم ورحمة الله وبركاته. أسعد الله جميع أوقاتكم بالفرح والخير والمسرات. سلام عليكم والسلام يقدم، يرق له قلب ويشدو به فم. طبتم وطاب مسعاكم، أهلا وسهلا ومرحبا بكم جميعا في هذا المؤتمر الدولي الذي تنظمه جامعة الإمام عبد الرحمن بن فيصل، ممثلة في كلية علوم الحاسب وتقنية المعلومات، والذي هو بعنوان المؤتمر والمعرض السعودي 11 للحوسبة عالية الأداء، لنمضي سويا بمشيئة الله تعالى لتحقيق أهداف وتطلعات هذا المؤتمر، والذي يهدف لتحقيق رؤية المملكة 2030 في مجال الحوسبة عالية الأداء، ولنفتح آفاقا جديدة لتبادل الخبرات العلمية والتجارب العملية، ولتعزيز الشراكات مع الهيئات المحلية والدولية ذات العلاقة في مجالات الأبحاث الطبية، الذكاء الاصطناعي، البيانات الضخمة، الأمن السيبراني، والحوسبة السحابية. خير بداية لكل بداية، كلماته نور، وإن له لحلاوة وإن عليه لطلاوة، وإن أعلاه لمثمر وإن أسفله لمغدر، وإنه ليعلو ولا يعلى عليه. هو القرآن الكريم، آيات من الذكر الحكيم، يتلوها عليكم القارئ الطالب محمد الشاذلي.
السلام عليكم. أعوذ بالله من الشيطان الرجيم. إن الذين قالوا ربنا الله ثم استقاموا تتنزل عليهم الملائكة ألا تخافوا ولا تحزنوا وأبشروا بالجنة التي كنتم توعدون. نحن أولياؤكم في الحياة الدنيا وفي الآخرة ولكم فيها ما تشتهي صالحا وقال إنني من المسلمين ولا تستوي الحسنة ولا السيئة ادفع بالتي هي أحسن فإذا الذي بينك وبينه عداوة كأنه ولي حميم وما يلقاها إلا الذين صبروا وما يلقاها إلا ذو حظ عظيم.
حفلنا الكريم، والآن مع فيديو تعريفي عن المؤتمر. يتفضل سعادة عميد كلية علوم الحاسب وتقنية المعلومات ورئيس المؤتمر الدكتور عبد الله بن محمد المهيدب لإلقاء كلمة اللجنة المنظمة للمؤتمر، فليتفضل مشكورا.
بسم الله والصلاة والسلام على رسول الله سيدنا محمد وعلى آله وصحبه أجمعين. معالي رئيس الجامعة الأستاذ الدكتور عبد الله بن محمد الربيش، سعادة نائب رئيس الجامعة البحث العلمي والابتكار الأستاذ الدكتور فهد بن أحمد الحربي، سعادة نائبة رئيس الجامعة للتطوير والشراكة المجتمعية الدكتورة نهاد بنت عبد الله العمير، أصحاب السعادة العمداء والعميدات، المشاركين والضيوف الكرام، زملائي وزميلاتي منسوبي الجامعة، أبنائي وبناتي طلبة الجامعة، السلام عليكم ورحمة الله وبركاته. نيابة عن كافة منسوبي زملائي وزميلاتي بكلية علوم الحاسب وتقنية المعلومات واللجان المنظمة للمؤتمر والمعرض السعودي ال11 للحوسبة عالية الأداء 2022 تحت شعار استخدام الذكاء الاصطناعي لتسريع وتحسين الأبحاث الطبية، أتقدم بخالص الشكر والعرفان لمعالي رئيس الجامعة على رعايته الكريمة لهذا المؤتمر وعلى دعمه الدائم لكافة فعاليات كلية علوم الحاسب وتقنية المعلومات. فخورين باستضافة الكلية لهذا المؤتمر في نسخته ال11 والبناء على نجاحاته السابقة، ويأتي اختيار عنوان المؤتمر ليعكس أهمية التحول الرقمي والذكاء الاصطناعي في مواجهة التحديات الطبية. ونفخر بإطلاق الجامعة لأول برنامج بكالوريوس للذكاء الاصطناعي على مستوى المملكة في عام 2019. وكذلك نفخر بوجود أحد أعرق الكليات الطبية على مستوى المملكة بالجامعة بتاريخ يمتد إلى أكثر من 45 سنة. وأيضا يوجد تعاون مميز بين كلية الحاسب وكلية الطب في تطبيقات الذكاء الاصطناعي في المجال الطبي. حرصت اللجنة المنظمة في هذا المؤتمر على دعوة العديد من أبرز الشخصيات من خبراء وتقنيين ومختصين ومهتمين والممارسين الصحيين إلى جانب دعوة الكيانات التقنية والطبية من داخل المملكة وخارجها، حيث يشارك في المؤتمر نحو 50 متحدث يمثلون دول عدة منها الولايات المتحدة الأمريكية، بريطانيا، فرنسا، ألمانيا، هولندا، إيطاليا، وخبراء سعوديين ومن دول خليجية وعربية، ويمثلون قطاعات حكومية وخاصة يقدمون 7 جلسات رئيسية و24 محاضرة علمية وجلسات نقاش و5 ورش عمل، وبأكثر من 800 مختص ومهتم سجلوا لحضور هذه الفعالية. كما اهتمت اللجنة المنظمة بأن يكون هذا المؤتمر مواكبا للتطورات العالمية في مجال الحوسبة عالية الأداء من أجل مواكبة التطورات التقنية عن طريق مناقشة أهم القضايا لتطبيقات الذكاء الاصطناعي في المجال الطبي، واستعراض أحدث الممارسات والبحوث الطبية العلمية، وتحقيق التواصل بين الخبراء والباحثين والمختصين والمهتمين للعمل على استيعاب التطورات التقنية السريعة اللي تشهدها العالم، واستفادة من تجارب ناجحة ومحاولة إيجاد الحلول الكفيلة بمعالجة مشكلات التحديات التي تواجه القطاع الطبي. حيث يصاحب المؤتمر هاكاثون تطبيقات الذكاء الاصطناعي لتحسين الرعاية الصحية بمشاركة 32 فريق يمثلون 14 جامعة سعودية، ومسابقة أفضل ملصق علمي حيث استلمت اللجنة المنظمة 49 ملصق، وتم اختيار 18 منها للمشاركة في المؤتمر لاختيار أفضل ملصق علمي في لتحقيق أهداف المؤتمر. قد تم دعوة أبرز وأشهر الشركات والجهات والقطاعات الحكومية في العالم العامل في مجال الحوسبة عالية الأداء لعرض ما لديها من آخر التقنيات، الأمر الذي يساهم بإذن الله في المزيد من المعرفة والخبرات والتجارب والممارسات الحديثة للوصول إلى مستوى متقدم لكل من يشارك في هذا المؤتمر. في الختام يسرني مقدما أن أرحب بجميع الحضور في المؤتمر والمعرض السعودي ال11 للحوسبة عالية الأداء، متمنيا بأن يكون لهذه الدورة من المؤتمر التأثير الإيجابي إن شاء الله وتقديم الفائدة المرجوة تقديمه. في نهاية هذه الكلمة توجه بالشكر الجزيل لكافة اللجان المنظمة، والشكر موصول لكافة الرعاة والداعمين والمشاركين والمشاركات لكل من ساهم في نجاح هذا المؤتمر. والسلام عليكم ورحمة الله وبركاته.
كل الشكر لصاحب السعادة الدكتور عبد الله بن محمد المهيدب على هذه الكلمة. نشهد اليوم بشكل واضح ما تبذله المملكة من جهود جبارة لاستخدام التقنية، والذي يعد خياراً استراتيجياً لمستقبل المملكة. والآن مع الكلمة الافتتاحية لمعالي رئيس الجامعة الأستاذ الدكتور عبد الله بن محمد الربيش، فليتفضل مشكورا.
طيب، بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. ضيوف الكرام، الأخوة والأخوات أعضاء هيئة التدريس في الجامعة، السلام عليكم ورحمة الله وبركاته. يعني بادئ ذي بدء نرحب بهذا الجمع المبارك، مثمنا وبتقدير عال كل من شاركنا بفكره وعلمه وخبرته، وحظينا بشرف مشاركته وإثرائه لهذا اللقاء، فأهلا وسهلا بالجميع في رحاب جامعة الإمام عبد الرحمن بن فيصل. وأشكر لكم استجابتكم دعوة اللجنة المنظمة ومشاركتنا خبرتكم وتجاربكم. الحضور الكريم، امتدادا لدور الجامعة وترجمة صادقة لرسالتها في خلق وإيجاد فرص اللقاء والتبادل التجارب والخبرات، سعت الجامعة ممثلة بكلية الحاسب الآلي وتقنية المعلومات لاستضافة أعمال المؤتمر والمعرض السعودي للحوسبة عالية الأداء 2022 في دورته 11 بعنوان استخدامات الحوسبة عالية الأداء والذكاء الاصطناعي في الأبحاث الطبية. ويأتي عنوان هذا اللقاء وبرنامجه العلمي ومحاوره المختلفة متوافقا مع توجهات الجامعة ومع وهويتها البحثية واهتمامها بالرعاية الصحية والتقنية الحيوية، ومتسقا مع الجهود الوطنية في التحول الرقمي في القطاع الصحي كأحد مستهدفات الرؤية. حضور الكريم، لا شك في أن التطور والتغيرات المتسارعة في المجال الصحي قد أحدث قفزة كبيرة في الممارسات الطبية المختلفة كالعلاج والتشخيص وطرق الوقاية، وكذلك في إدارة المنشآت الصحية والسجلات الطبية والترميز والتصنيف. وتولد نتيجة لذلك كم هائل من المعلومات المتراكمة ومن مصادر مختلفة يصعب أرشفتها وتبادلها واسترجاعها ومعالجتها، وبالتالي فإن الاستفادة منها دون اللجوء إلى قدرات وممكنات تملك خصائص السرعة والدقة والجودة العالية كاستخدامات الحوسبة عالية الأداء وتطبيقات الذكاء الصناعي يصبح صعبا. لذلك كان استضافة هذا اللقاء الهام والذي يأتي ضمن جهود الجامعة لبناء جسور التواصل مع الجهات ذات العلاقة محليا وإقليميا وعالميا، فضلا عن عقد الاتفاقيات الاحترافية وتبادل الخبرات بالتنسيق والتعاون مع الجامعات والشركات الجامعية. وتأسيس على ما سبق، حرصت الجامعة ممثلة باللجنة المنظمة على توفير مقومات النجاح من خلال قاعدة عريضة من المشاركات والتنوع في الأبحاث والأوراق المطروحة، وهذا بإذن الله كفيل في أن يجعل هذا اللقاء ناجحا ومتميزا ويجعلنا أكثر ثقة فيما سينتهي إليه من توصيات ستكون بلا شك لها انعكاس إيجابي على الممارسات والخدمات الصحية. شكرا جزيلا لجميع اللجان المنظمة لهذه الجهود الموفقة والعمل المتفاني في تنظيم هذا اللقاء، وأسأله تعالى أن يكلل جهود الجميع بالنجاح نحو لقاء ذو طرح رصين ونفع وفير وفائدة جمة، وأن يوفقنا من أجل خدمة وطننا ونمائه، وأن يحفظ بلادنا وقيادتنا ويديم عليها دائما الأمن والأمان. والسلام عليكم ورحمة الله وبركاته. I want to take this opportunity as well, and I wanted to welcome our guests and attendees to this conference, and thank you very much for answering the invitation of the organizing committee, and thank you also for coming all the way to share with us their knowledge and their experience. Good luck, wish you all the best, and looking forward for the recommendations that I'm sure will have its influence in our practices in computer science as well as in health care and health technology. Thank you very much.
كل الشكر لصاحب المعالي رئيس الجامعة حضورنا الكريم، والآن مع تكريم الرعاة وشركاء النجاح فليتفضل صاحب المعالي مشكورا. والآن مع تكريم الراعي البلاتيني للمؤتمر شركة انتل فليتفضل ممثل الشركة الأستاذ أحمد عبد الجبار ليتسلم الدرع. والآن مع تكريم الراعي الذهبي للمؤتمر شركة HPE فليتفضل ممثل الشركة مستر فيليب لاتشام ليتسلم الدرع. شركة لينوفو and AMD فليتفضل ممثل الشركة الأستاذ علاء بواب. شركة ديل EMC فليتفضل ممثل الشركة الأستاذ أسامة عبيدة ليتسلم الدرع. شركة أتوس فليتفضل ممثل الشركة الأستاذ عمر القاضي. والآن مع تكريم الراعي الفضي للمؤتمر شركة كورنلز نتوركس فليتفضل ممثل الشركة مستر إيان واردروب. شركة ألتير فليتفضل ممثل الشركة مستر بلا مورغان رامزي ليتسلم الدرع. شركة باس داتا فليتفضل ممثل الشركة مستر لوي إيدي ليتسلم الدرع. شركة ألترا انفورميشن تكنولوجي، فليتفضل ممثل الشركة الأستاذ بلال أحمد. شركة داتا دايركت نتوركس، فليتفضل ممثل الشركة مستر لورنت ثيرز. حفلنا الكريم، والآن تبدأ أولى جلسات المؤتمر، ورئيسة الجلسة دكتورة سمية الجميل.
لا مو اوكي. Assalamu alaikum wa rahmatullahi wa barakatuh. I would like to welcome you all in IEU HPC conference. It's such a pleasure to chair the first session under the title, The Role of HPC in Medical Research. Nowadays, increasing population density and the healthcare costs are putting pressures on the life sciences industry to treat more patients, more cost effectively and with a better results. At the same time, advances in genomics, bioinformatics, microscopy, and imaging, medical imaging, and many more areas have creating an avalanche of data that can be used to improve patients' outcome. Advanced computer technologies such as artificial intelligence algorithms running on a high-performance computing HPC system are the key to using medical data to save lives and protect health better, faster, and with a lower cost. In this session, we will have 5 talks about the role of HPC in medical research, and last 30 minutes will be allocated for open discussion and the audience questions by scanning the QR code. Let's together welcome our speaker today. To join me on the stage, Mr. Philip, the Director of HPC and Intel Company in Europe, Middle East, and Africa. Dr. Yahya Bukhari, Associate Research Scientist in King Abdullah International Medical Research Center. Mr. Zishan Kamal Siddiqui, HPC AI Technical Sales at Lenovo Middle East and Africa. Mr. Muhammad Al-Arawi, Research Specialist in King Abdullah University of Science and Technology. Our first speaker today came to show us Intel's Hpc AI strategy and the new innovation, including the latest Intel scalable processor, data center GPUs, and powerful software tools. Let's accelerate the next era of innovation in Hpc AI with Mr. Philip.
Good morning. Thank you very much for the invitation, and I'm very happy to be here today. I'm Jean-Laurent Philippe from Intel, and I'm the director for HPC in Europe, Middle East, and Africa. I am especially happy to talk here about HPC and AI in the domain of medical research, because Intel's mission is enhance the life of every person on Earth. So we know that HPC and AI have been really important for the COVID medication. Intel contributed to it, and Intel contributes with computer science, processors, software, application development to provide new solutions, faster solutions, to get to new solutions for medication in the world. That's one of the parts of Intel doing. Of course, we do plenty of other things, but today I'm going to focus on where we need to go in the future towards zeta scale to get the level of computing performance that is needed to tackle all of the medical issues that we are facing today. But first, let me come back to something which is really changing the world today. We need to be conscious about how much energy we are consuming to manufacture, transport, and use all of the equipment that is needed to reach the solutions in medical research. Intel is working on it, and we are looking at how much emission we are creating. First, by making the products, as you can see at the top, by operating it, and through the ecosystem. And you can see that it's really the ecosystem that is using a lot of energy. So we all need to address this issue, which is very difficult, of reducing all of the emissions at all stages. Unfortunately, this will be very complicated because the demand for computing performance is increasing at a stage that we have never seen before. It is clearly far outreaching Moore's law, and it's driven heavily by AI-based algorithms, and it's expected to keep on growing. The energy consumed to achieve a certain computing result is expressed as the product of the power and the time required to complete the task. It is simple, but there are several factors that impact that result. Some of them are the clock frequency, the voltage, and of course, the time spent waiting for data. Interestingly, some of these compete against each other. Typically, a higher frequency can get you to a faster result, but it may consume more energy. So we really need to apply the first principles across silicon design, software, and systems to minimize the energy consumption. And we need to all work together to achieve that. Let's compare data center computing efficiency versus the car efficiency. In a gasoline car, about less than a quarter of the energy is transferred to the wheel. The rest is wasted. In an electric car, it's about 80 to 90%, which is transmitted to the wheels. How do the data centers stack up against cars? Not so good. As you can see, less than a quarter of the energy on average is used to really create the compute capabilities. The rest is used for functions like cooling. Of course, they are critical. They are really needed. But we are all here about high performance computing, not high performance cooling or lighting. So we need to do better. To do so, we need innovation across silicon, software, and systems. Let's start by diving into silicon. The traditional CPUs, like the Intel Xeons, are responsible for running the vast majority of workloads. Xeons will continue to tackle the bulk of general purpose tasks. Emerging high demand workloads such as AI, encryption, and data analytics benefit enormously from specialized or alternative architectures. With optimized architectures for these workloads, we can improve the performance by orders of magnitude. And we can, at the same time, decrease the energy demands. We can more or less break these architectures into four. Scalar for the three typical CPUs that can also do vector. Matrix, mostly for the GPUs. But you also know that Intel has pre-announced the fourth generation of Intel Xeon processors, codenamed Sapphire Rapids, that is embedding the advanced matrix extensions that will also be capable of doing matrix multiplications and additions extremely efficiently. So that will help tackle this problem of energy. And the spatial architecture is more the FPGA type of solutions. So if we can put those different hybrid architectures working together and addressing the right part of the application that is needed to find the solution, we will be able to make the best use of the energy that is available. So we need to make sure that the workloads are really taking advantage of this. And with the new packaging technologies from Intel with the 2.5D or 3D stacking of different solutions on top of each other, then we can look at solutions where there will be more hybrid architectures onto the same package. Let's call it a certain type of processors. That will be yielding dramatic improvements in bandwidth, performance, and power efficiency. course, this will require some work at the software levels. And you know that Intel is not only working on hardware, but I will show you also working a lot on software. So that's painting the future of the theoretical solutions, but let's be a little bit more practical. At the top of this slide, be reassured that Intel will be continuing to provide the Xeon line of products with the fourth Intel Xeon scalable processor generation, Sapphire Rapids, that we are talking about on a regular basis, giving new information. And we have just announced some new information at ISC 22. There will be Intel Innovation where we will be giving again new information. In the coming years, we will have a refresh of this line of product with the Emerald Rapids processor, followed by the Bright Rapids. Next row, or we call it swim lane, you can see that we are also looking at solving a problem which has been hitting you and us for a long time now, which is the memory wall. And we are introducing the HBM high bandwidth memory into the Xeon processor with the new Sapphire Rapids with HBM technology. And in the coming years, there will be more of these products in this swim lane. As I said earlier, some workloads benefit from matrix type of environment, like the GPUs. And Intel has been talking a lot about the Ponte Vecchio GPU that will be followed in the coming years with the Rialto Bridge. And we also have dedicated hardware for AI, both inference and training, ASICs that are called Gaudi and Gaudi 2. And Gaudi is already available for usage. And you can see a combination with Falcon Shores coming in the next few years that I will talk about, a conversion of CPU and GPU. Let's talk a little bit about Sapphire Rapids with HBM that is providing 64 gigabytes of high bandwidth memory. It also keeps all of the good things that the Sapphire Rapids processor is bringing, and especially the AMX technology that is embedded directly into the libraries that are called by the TensorFlows or PyTorch or the likes, directly to provide extremely high levels of performance for AI. And there are some other accelerators that are embedded directly into the processor, typically for cryptography or data streaming. Ponte Vecchio, our first AI and HPC GPU, is a monster of over 100 billion transistors, equipped with 128 gigabytes of memory. And that's where it makes a big difference, because the more memory, the more data you can crunch. And it will be installed in the Aura machine at the Department of Energy in the US, reaching a level of over 2 exaflops of peak performance. Moving into the future, Rialto will be an evolution of Ponte Vecchio. It will have about 25% more cores. It will be using new levels of manufacturing that will take advantage of new manufacturing and packaging technologies. It will yield more flops, both for HPC and AI, and a balanced increased bandwidth. And it will be on a similar OEM solution, so that you can slide in and out a direct solution with 4 PVCs, Ponte Vecchios, with 4 Rialto Bridge solutions. Earlier this year, our CEO and our GM and VP of the Accelerated Computing Systems and Graphics Group at Intel, Raja Koduri, has announced Falcon Shores XPU that will be coming in a few years. We know that the discrete solutions are great, but they have some limitations. Typically, data movement is really hitting the level of performance and therefore of energy. So Falcon Shores will exist, as you can see on the left, as a CPU tile-based solution, or to the right as a GPU tile-based solution. But then we can mix the CPU and GPU tiles to make it in the middle an XPU. And those different versions with a mixture of x86 and Xe cores will really reach the level of performance that we need at that time, which is more than 5x the performance per watt, the compute density, and the memory capacity and bandwidth. So we will have a very, very balanced solution. This will be achieved with advances in process technology, I/O, packaging, and it will enable a simplified programming model. Silicon alone is just sand. So now we need to look at software to bring it to life, with a focus, of course, on programmability. Intel's software strategy is to do the same as for hardware. We bring ingredients using some standards like USB, PCI, CLX, CXL, etc. So there are plenty of hardware standards that we are developing and implementing. On the software side, it's the same. We want everything to be open, standard, and based on trust. And as you can see here, we have some layers that are reaching the hardware. That's the lowest level. And above that, we have provided already for now 3 years, because we announced it at Supercomputing 19, the one API development environment. And the one API development environment is here to accelerate cross-architecture, cross-vendor programming. As I said, it is open, standard, and then it can be used to develop applications that then can run efficiently on any hardware. CPU from Intel, GPU from Intel, CPUs, GPUs, FPGAs from Intel and from our competitors. As we all know, there is a significant amount of code which has been developed using CUDA, and Intel has developed a tool called, let me pronounce it my way, Cyclomatic, based on SYCL, which is the standard that we are using to program to, which is based on C++. And this tool is taking CUDA source code and is translating it automatically to SYCL. And as I said, SYCL is the level of programming in source code that can be used to then compile to different architectures. It is open source and it is available on GitHub. So that's for the HPC side of the house. For the AI side of the house, because as you know, Pontevecchio, as I said, is dedicated to do HPC and AI. We have in our CPUs, like the Intel Sapphire Rapids or the Intel Ponte Vecchio GPU, the levels of instructions for matrix multiplications that are then embedded into the libraries, and the APIs and tools like TensorFlow, PyTorch directly call these libraries without you having to rewrite your code, so that it takes advantage of all of the hardware that is available. No code change. And we know that it is very important to be able to port and reuse code. So I've covered the heterogeneous architectures and how to program it. Now let's bring them together and see some performance numbers. HPC and AI go together. And you can see here that with the coming Sapphire Rapids processor, doing DeepCam or CosmoFlow training, then we are reaching about 3x the performance of the AMD 7763 processor, or higher performance than the NVIDIA A100. Remember that I said that there is AMX in Sapphire Rapids, and that makes a big difference. So you don't need to use necessarily some accelerators like GPUs to do that. In terms of HPC workloads, compared to the current generation of Xeon processor, the third generation, codenamed Ice Lake, then you can see 2 to 3x the performance. And with HBM, you can reuse your code without any change and taking advantage of the memory bandwidth without having to rewrite your code. And in many cases, you don't even need DDR because there is memory directly into the CPU. And for the GPUs, we are having in FSI, in finance, as well as in training, some very high level of performance, as you can see here. Manageability is very important, and we have the Intel XPU Manager that we have announced at International Supercomputing in June, which is a solution for local and remote monitoring and managing of the data center GPUs. It is open source and it is available now. In terms of systems, we really need to look at the energy efficiency. And as I said earlier, the same subsystem can be used to host Ponte Vecchio-based and Rialto Bridge-based solutions. In terms of footprint efficiency, DAOS, our solution for parallel storage, distributed storage, brings a high level of solution and performance, reducing the physical footprint and therefore cutting down the power efficiency. And compared to Lustre, as we have worked on with Professor Kalija at the University of Cambridge, you can see that DAOS is reaching extremely high levels of performance, 7x the level of performance. Scalability is super important, and I will end up on this. We are asked by our users to reach a level of zeta scale, so 1,000 times what we have today, by the year 2027. This is a huge challenge that we are tackling, looking at all of the levels that we can work on: architecture, power and thermals, process, manufacturing in our fabrication units, packaging, and of course, memory and I/O. That was a lot, I know, but you can see that Intel is really reinventing itself with our new CEO, Pat Gelsinger, working on all of the future of technologies and solutions. So as I said, we have all what we need on silicon for the coming years. In terms of software, we are providing all of the underlying tools that will be facilitating the development of applications. And around the HPC supercomputer, access to data is super important, and that's why DAOs is something that we are developing, which is very important. Thank you very much for listening to me.
Thank you, Mr. Philip, for the interesting presentation. Before moving to the next speaker, I would like to welcome Mr. Novo Genomics to join us on the stage. Thank you. Laboratory image analysis is among the most important skills needed for the diagnosis of genetic disease. Applying AI methods and algorithms to lab clinical images not only helps in saving time, but also leads to more accurate results. Our next speaker will talk more about this topic, so let's welcome Mr. Yahya Al-Khan.
Assalamu alaikum. Today, I will talk about application of artificial intelligence in cell genetics. So basically, what I'm trying to do is trying to bring automation into chromosome analysis, as there is an automation in X-ray analysis. So I came from a medical technology background. I worked in cell genetics for 5 years. Then I shifted into computer science and engineering. So basically, I'm selling my work to me. Should I start on? Okay. Oh. How to go back? Okay, today I will talk about AI or application of AI in chromosome analysis. So basically, I'm trying to bring automation into say genetics or chromosomal analysis, as there is an automation in radiology and X-ray analysis. So again, I work in genetics lab. My background is medical technology. I work in the genetics lab for about 5 years. Then I shift into engineering and computer science. So my work is basically I'm trying to convince myself that it's working. So I am the customer and I'm the inventor. So first I will give you a brief introduction on how genetics lab works, then their problems, the problem we had there, and then how I propose some solution to that. So the journey starts when physicians order bone marrow samples. It's very painful procedure. They stick a needle inside the bone to withdraw some bone marrow. So you don't want the patient to go through that many times because of the poor analysis. So after that, they send the sample into the lab and then they put it in a culture, few days, few chemicals, then they extract the cells, then they put it into a slide. And then after that, they analyze those slides under the microscope and take images and try to do karyotyping. So this is what they see under the microscope. They see those chromosomes. As you can see, different quality, different length, different samples. And this is basically a genetic material. So they analyze the chromosomes under the microscope. Afterward, they do the karyotyping using some software. They arrange it. As you know, as a human, you have 23 pairs of chromosome. So if you look through this image, it's very painful procedure for the technologist because they have to analyze line by line, band by band. They don't want to miss anything. If they do this all day long, so it's error prone, it's time consuming, and it's also expensive. Because of redundancy, they tend to do error, and even when they find the abnormality, it's very difficult to write the report. So, for example, there is an abnormality here in chromosome 15. There is a genetic material came from chromosome 22 transferred to that chromosome. And when they found this abnormality, this is big abnormality, it's not easy to miss, but sometimes it's very small. So they report it as you see there below. So there is an automation in the lab. So the culture is being automated, the slide dropping is automated, staining the sample is automated. The things that's not automated, that is the analysis. And as I said, chromosome is just DNA packed, like a thread's being packed. It has different length, different size, different shape. So just to imagine the difficulty of auto-analysis, this is chromosome 7 below. As you can see, this is the same chromosome with different shape, different color, different length. So it's really difficult to find to define a class for a given chromosome so that you can define the abnormality or detect the abnormality. Another example, this is supposed to be the same chromosome, chromosome 2. As you can see, different qualities, really difficult. And you can imagine they stare at this all day long and try to analyze band by band to find any abnormality or any missing genetic material there. And there is the ISCM, what they do is trying to map each line in a chromosome. For example, as you see below chromosome 7, they're trying to map it. So chromosome 7 has different length, depends on when they catch it, but depends on when they catch it, they have different lines or different, you can imagine this as a barcode, and you have to compare two barcodes at the same time. So there is automation in scanning, in captioning, but enhancement is manual, karyotyping is manual, analysis also manual. So the solution I propose is I used multiple solutions. I use CycleGAN, pixel to pixel. Also, I use style transfer. So as you know, CycleGAN is trying to transfer image from, for example, you want to transfer zebra to a horse, as you can see from left to right. But the catch there is it has to be the same size. So what I did, I just extracted the chromosome with the same size, like thousands and thousands of images with the same size. I extracted them, and then I applied CycleGAN, and you see I divided the classes into poor and good morphologies, as in zebra to horses. So I put the poor morphologies in a class with the same length and good morphologies in the class with the same length. And the result, as you can see, I converted the left poor image to the right good image. And here a closer enhancement, as you can see, chromosome 2, before and after, and so on. And here a big picture of chromosome 8. As you can see, it's very sharp now, it's easy to analyze. So another thing I wanted to do to make it even easier, I wanted to convert those images into cartoon, to barcode, so that it can be analyzed by the machine. To do that, I did pixel. It came to my mind: can I use pixel to pixel? Can I like combine two images and to get better images? This is what came to my mind. And what I did, I computationally generated the chromosome like barcodes, and I modeled it to bend it like the chromosomes. And then I combined the two images using style transfer, and this is the result I get. You can see that there is band, and again, it's easy to analyze when you compare it to the first image. But I wasn't happy about the result. So what I did, I had to do this solution. While it's very difficult, I had to draw thousands and thousands of images using Photoshop, drawing each single line, so that I wanted to apply pixel to pixel. And when I did that, see the result of transferring the images from very poor. It's not, they consider in cell genetics that this is very good looking in the left chromosome. But then if you look in the right, this is how I transfer the images using pixel to pixel to this very, very sharp chromosomes. You can see band by band, and you can compare it very easily, and you don't have to have very heavy training to do this analysis. So again, this is another example. You can see the chromosome 8 that I enhanced, then I converted to be sharp lines. So this sharp lines, if you have its twin chromosome, it's easy to analyze, and it's easy to find any single band deletion, which is very critical when you want to report the results. Now I'm in a phase of straightening the chromosome, because I don't want any bend, because if it's straight, it can be called as a barcode, and then the computer will be easy to analyze and it's easy to compare with its twin. After that, transferring all chromosomes into a barcode, it will be easy to analyze. As I said, it's with its pair, and that's it. And this is the pattern of my work. Thank you.
Thank you, Ilya, for your presentation and pointing about the importance of analyzing medical images. So the volume of data generated from biological source has increased massively. Biomedical research within Saudi Arabia needs focus in exercising fair use of data and fair access to Hpc resources to further achieve the goals of improving human life. So let's know more about biomedical Hpc infrastructure in Saudi Arabia with Mr. Mohammed Al-Harab.
الصوت مو واضح.
Okay, Assalamu alaikum everyone. Good morning. I hope by the end of this talk, I can convince you for data sharing. Okay, again, I came from the background of data generation and biological data, in addition to computational science. So actually, I'm a proxy between biological data generation and biological data analysis. Let me first of all give you first an overview about the infrastructure, about HPC in Saudi Arabia, challenges and why biomedical data is critical and important. At the same time, what do we expect and the proposal of the Saudi biodata depository. And finally, we end up with some conclusion, but I need to set up my time. Okay, first of all, about the academic growth in Saudi Arabia. If you can notice, the number of academic institutions in Saudi Arabia since the year 2000 has increased significantly, and it is actually increasing by spinning out a new institute. This data is driven from the Ministry of Education data, and this is the number of scholarship. This is driven from Ministry of Education and also from the UNESCO dataset. This is the number of students studying abroad. And you can see since the King Abdullah Scholarship Program, and the number of scholars has increased significantly. And this figure shows the number of postgrad per 100,000 population. For each 100,000 population, there is a more than around 600 individual with a postgrad degree. That means there is more researcher than actually assistant or associate professors in universities, meaning we have more volume of research staff, and that does not include students in Saudi's universities. These are talking only abroad. And if you can look on HPC presence in Saudi Arabia, it is extremely very clear that HPC is only centralized in 3 regions: in Eastern Province, Central, and in Western Coast. And these actually represent Saudi Aramco, KAXT, and King Abdulaziz University and KAUST, with very limited, or there is a connectivity actually connecting all institutions, but with the industry being away. And performing on HPC landscape in Saudi Arabia since 2009 up to 2018, we marked the year 2015-16 as the best, where we had 7 HPC registered in the top 500. That's across Saudi Arabia. But you will be surprised to see the fingerprint of Saudi Arabia in the global domain. This is driven from the most recent updated data set for top 500. And you may ask a question about how does the academia share look like? This is the list of the 7 HPC. And you can see that 6 of those HPC actually industry. And only 1 is belonging to the academic institution. So this is a quick glance about the HPC presence in Saudi Arabia. Now let us focus on why actually we care about biological data, or why actually biological data is quite important. This is the very simple graph illustrating the drop of cost of generating biological data and the volume of the data that's being generated. This is a little bit outdated, but again, I'm not the only one showing Moore's law here. You can see the decrease of cost per human genome sequence since the announcement of the project 2003 till now 2019, where you are expected to achieve below $1,000 a very good complete human genome. And this is the dramatic decrease since the announcement of the result, where the project cost $3 billion. Now it's not $100, it's between the $300 to $1,000, where you can actually produce a whole genome data set. And this is expensive data in order to manage and store with a lot of limitation. And this is the volume of data actually now being deposited in public data depositories. And this is only showing the European Bioinformatics Institute sequence archive. And this is the growth of different databases, where y-axis shows the sequence by million, and in the x-axis showing the years. And the red line shows the user average axis, and the blue line indicates the sequence number. So there is a very sharp increase in the data volume, and it makes just very simple format of the whole image. This is how it looked like in reality. And this is only focusing on biological data. So how, as a scientist, can actually make use of this? This brings us to the zettabyte scale. There is an expectation that biological data growth expected to it will be even more than YouTube videos in the coming years. And 2025 expected more biological data. So one estimation that the data is doubling every 7 months, 12 months, 18 months. With the very robust indication says that by 2025, and the red line, the data, biological data deposited will be, this is storage. We're not yet in compute. Okay, this is storage. We will reach zettabyte scale. So that actually brings a very important I/O problem, which is actually biological data tend to be not all actually numerical or like CFD kind of workloads. It's more of a very intense compute. So there is a high use of RAM and high use of actually connectivity and also disk read and write. So scientists basically will generate data, store data, compute, and do it endlessly. That brings us to a very important, significant piece of literature that actually was published, citing more than 25,000 published and cited tools for bioinformatics. See the growth of tools that have been developed, and this is in the public domain. We're not yet exposed to not published tools. So the change in the paradigm shift, actually moving from experiment, data, analysis, this is actually the regular workflow, into becoming this, you generate or you utilize data to do analysis, and then you design a lab experiment to validate your finding, because there is a very sheer amount of public data that is available. Which brings me to the second point of this talk is, why do we need a Saudi research data depository, especially for biomedical data? You know, omics and biological data are very rich. There is so much features within this biological data. So pretty much you can extract and train models in these data, since they are very descriptive of living systems, okay? So why actually we need to take this action? Because there is a very sheer amount of volume of data that's been dispersed with PIs. There is no data depository within Saudi Arabia that can accommodate this data for fair use. Findable, accessible, interpretable, and reproducible. There is no access to national database on genomic level. There is a very limited reuse and data exchange, and there is a very limited presence on a global research frontier. So these motivation brings us to actually a very fundamental problem. Usually, whenever we receive a research grant, we generate research data, we find results, we publish a paper. But this is it. That's where it ends. However, if we adopt it to fair data principle in this Saudi data depository, we will be able to make this data usable for secondary research. So hence maximizing the fair access to data, maximizing the value of research money. So the research money you are spending actually is not stationed on the first project. The fair data access allows you to access the second and third and fourth project. And sometimes for cases like diabetics in Saudi Arabia, anyone who is successfully able to generate a very good detailed data for diabetics patient and genomic level, this data should be available for any other secondary research. Sorry, I have to rush a little bit. So in order to have a very fundamental and useful HPC infrastructure across the Saudi Arabia, these are the three main domains that this HPC infrastructure cater for, which is precision medicine and human health, genomic and sequence data banks, plant and any animal omics data set. And this is necessary to enable translational research by enabling education and training, enhancing the connectivity across all academia in Saudi Arabia, creating a data depository, and adopt the concept of federation. So all Saudi University can be part of a big HPC federation that cater for everyone. So there is no necessity to have HPC enclosed within certain regions. And this actually allows access to data from different institutes with very maximized use of research data. And at the end, this requires some investment, actually, and very strategic decision, which at the end of the day will enhance the global presence of data. Since my time is up, at the end, I just want to mention that a national infrastructure will actually enable more access to HPC. And I'm referring to e-infrastructure. each institute is happy with their HPC. At the end of the day, they have infrastructure that connecting everyone together. And we should enable for data depository and management to maximize the secondary use of data. And hopefully by this, we can create a science gateway in Saudi Arabia for the whole MENA region connecting Africa and Europe, since we are centralized between Africa and Europe. And by this, I think adopting the fair data principle will be very crucial, and secondary use of data and data marketplace. Thank you so much.
And pointing the importance of using the massive biomedical data. And I believe analyzing massive biomedical data needs a special tool. Now, Novo Genomics researchers analyze a whole human genome in 53 minutes, and the whole exome is about a minute. In standard cloud or environment, the same analysis usually takes 60 to 150 hours. So our next speaker will talk more about the genomics optimization and stability in Novo. So welcome, Mr. Nishan Kamal.
Alhamdulillah Rabbil Alameen, salatu wassalamu ala Rasuli Muhammad wa alihi sahbihi ajmain. My name is Ishan Kamal Siddiqui. I am from Lenovo, and today what I'm going to speak about something which Mr. Mohammed was talking about. Good that he has a presentation before me, and he talked about the importance of the genomics data, how important it is and how important it is for Saudi Arabia. And of course, you require special tools to help to increase the performance for that genomics data and to use the HPC skills on that one. And this is what I'm going to talk about today, is about the genomics optimization and scalability tool. We call it as a GHOST. Before moving to the tool itself, let's talk about the basics, what genomics is, what genome is, and something, so that we understand where the actual problem is, and then we'll point out to what the tool can does and how we can help in that one. So basically, genomics is the field of science that talks about the genome. So genome is completely a set of the complete DNA. Okay, and with that one, you get the subsets of the gene. Now, further ahead, if you further divide the gene, then you have the subsets, which is called the exome. So basically, the exomes are very small subsets of the complete genome. And of course, then you have the proteins that develop with these exomes. Now, where the actual things come up. So the study of sequencing the exome is basically known as the whole exome sequencing, which is known as the WES, which is, and the study for having a complete genome sequencing is known as the WGS. And as you can see, it is very important to have a study of the WGS as compared to the WES. The reason is that the whole genome sequencing will give you the complete information about the DNA of the body and helps a lot in that one. So the whole exome sequences is only approximately 1% of the data, which is easier to assemble, which is cheaper, but does not give you the exact results that you are looking for, especially for the medical research, for the pharmaceuticals, for different disease detection and everything. What you require is the whole genome sequencing, and there you require the more data, which Mr. Mohammed was talking about as well. You require more storage for that one. So what happens, and this is the same slide that he talked about. So ultimately, the price has reduced of sequencing the whole genome sequencing. The price has reduced a lot when it comes to from the day one until now. So now we have the technology available that can help us to do the whole genome sequencing in a very lesser price and a very efficient way. And this is what I'm going to talk about. So how does the genomics workflow works? You give the samples, like as a patient, if I want to have my genome to be sequenced, I'll need to give my sample through a blood or a saliva or something. It goes to a sequencer machine and it converts this into a digital form. That's called the primary analysis. Okay. Then comes the main part. The main part is the secondary analysis, where you do the genome analysis, where you have a reference genome and then you need to compare the different data results across each other, and you come up with the variants. These variants are very important in the medical research, so that you know exactly, like for example, you have a patient of a coronavirus, you have a patient of a flu, you have a patient of a dengue virus or something. How does it affect his DNA sequencing? What are the variants and what are these all infrastructure comes in? So HPC basically plays a part in the role in the secondary analysis, where you're doing the genomics analysis. There is a tool which is called GATK, widely used by the medical research people for this kind of analysis. So what we have done is we have taken that GATK software, we enhanced its performance, and we have taken it, run it on our HPC systems. Let's take an example of a pharmaceutical. So if a pharmaceutical company wants to have a drug for any disease to come up very quickly, the most important thing for them is to have these sequencing available. This is the most important data, because without that one, they can't do research on that. The challenges that they take is, this one sequence can take about 60 to 150 hours. And that's what about the software that I talk about. 60 to 150 hours. And imagine if you wanted to do the sequencing of thousands of people, or maybe some countries are going for the whole population as well. It's a very large time scale to do that one. Plus, it's not scalable. You have a lack of the expertise in HPC plus genomics, because you need both expertise together in order to work on that one. Of course, there are multiple workloads, and of course, there is no time for extra resources, something. So what does we come up as, which we call as Lenovo Ghost, or as is called genomics optimization and scalability tool. We took GATK, we have our researchers working in our company, and they enhance the performance of the software. And we come up with a combination of the software plus the hardware. Remember that every software need to run on the hardware, of course, okay? And if the hardware does not talk to that software very efficiently, there is no use of even a high processor or high GPU or something if it does not help the software to generate this performance. So what we have done, we have especially tuned the hardware. We have pre-configured the omics software, and we made it as a package, and that package we call it as Ghost package. Okay, that comes as a package where our customers for the medical research, they can purchase that one. So what we have seen, that these kind of applications are dependent on high cores. They require fast storage, especially the internal storage inside the servers. They require high memory. And of course, what we have done is we have optimized this bioinformatics package there. So when it comes, this package, the Ghost package comes in, it is pre-installed with all the necessary tools that are required for the application and for the HPC as well. So it has all the tools that you require to do your analysis and everything else. So what's the advantage for that? So what are these flavors comes in? We've got three systems. One, we call it as Ghost Base, Ghost Medium, and Ghost Plus. If you see, all of them have different processors, 40 core, 64 core, or 8 socket machine. You have different memory, you have different storages. Depends which one the customer would like, and everyone will have a different performance. So this package comes with the omics software, with the Ghost software, plus the hardware as well. How does the performance is? That's what the performance is. If you see the timing of per sample to do a whole genome sequencing, we have reduced the time from 50 to 160 hours to almost 47 minutes, which is amazing. Imagine the sequencing that would have taken around 50 hours. Now you can get that one in 47 minutes as well. So that means maximum what you can have per day, you can have 30 samples per day or 11,000 whole genome sequencing samples per year, which is quite very amazing. The good thing is it is very linear. So that means you have one node giving you this, this performance. You can have multiple nodes and you can run parallel of these sequencing. And of course, the timing is very efficient and then you can get more results per day as well. This is just a comparison of what we did, as I mentioned initially with the typical GATK software. As of now, it takes around 60 to 150 hours. The select solution around 11 minutes. We have a base and the Ghost Plus, which can go up to only 47 minutes. Now, is it very expensive? Is this something that a very highly paid software is required or something? Guess what? It does not require any accelerators. It does not require any GPUs. We work on normal servers. The previous slide that I mentioned, it's got only the CPUs, memory, internal storage, but not the GPUs. All right. So you don't require high accelerator or high price GPUs to run that stuff. This runs on the normal servers that we use in our data center very efficiently. It's just the efficient way that how we have designed that. Just another slide that how much per samples we are generating. We're gonna have some future directions as well. In future, we're gonna have servers with more number of cores, and of course, with more number of workloads. You can have different bioinformatics softwares that you can run. It's only not designed for the GATK. You can run other bioinformatics or other omics softwares as well, and will give you more enhanced. So we're definitely gonna have more enhanced performance once we are there. So what were the challenges and what we have done? The challenges for the genomics sequencing, it was slow. So we've increased the performance almost 240 times of that one. There was the profits, growth and funding. Of course, we have increased the growth for that one. There is an issue for not scalable. This system is scalable. Means once you have, you can start with one server as well, by the way, okay? And you can enhance it. You can have multiple of those servers connected with the interconnects and run as an HPC cluster. And you don't require extra or enhanced HPC skills. This is combined as an HPC skills plus the bioinformatics skills combined together. And as I mentioned that we don't use these GPUs or FPGAs, and we ensure the data privacy as well. Just to give you a few examples, what we have done worldwide, we started with Barcelona supercomputing, if you see that. So from 40 hours to 45 minutes, they have increased the performance of 53 times, from 40 hours to 45 minutes using our Ghost systems. This is currently running in the Barcelona supercomputing and then using it for the cancer and the other infectious diseases. Something in University of Delhi, they are using it not only for humans, it can be used for the plant breeding, for the improvement, for the crop growth as well. They increase the performance by 30% as well. There is another one, CSIR Institute in Genomics. This is what, again, they are using our systems as well. So it's quite very important. And of course, we'll be using it in worldwide. So what are we doing in Saudi Arabia? That's one question. And that's what Mr. Mohammed was talking about as well, that it's very important to have these kind of data available in Saudi Arabia and what we're doing. So our first project now, we are doing it with the Novo Genomics. We're going to have an MOU to be signed today. You guys are most welcome to join us. So Novo Genomics is basically a Saudi-based company. Their main aim is to bring in this technology into the country and to that do all the research work and of course generate the data for the health and wellness of the people. So we are working with them very closely. They will use our Ghost system. This will be the first Ghost system in Saudi Arabia and many more to come, inshallah. Thank you very much.
For the presentation, and we are happy to hear about the Novo Genomics. Thank you. Next speaker will provide us with a promising result and best practice in using King Abdulaziz University supercomputer to apply genetic medicine in clinics. So let's welcome Dr. Novo Genomics, Assistant Professor in King Abdulaziz University.
Okay, hello, everyone. Thanks for inviting me to this talk. I am Novo Genomics. I am from King Abdulaziz University. My background is computer science, but I am working for 4 years in clinical bioinformatics. And I am keen today to share with all of you some applications and problems and some also promising results in order to bring this research base into the clinic use. And I think this is the most important thing to do in nowadays is not just to keep doing the, data and generating data as Prof. Muhammad just mentioned. It's more about how to start using it in our clinical practice. So I would start my talk not with telling you the importance of doing a medical or genetic test, but I'll just show you a tweet by Prof. Fawzan Al-Freya. Just last week, he was talking about the 3 sisters who suffer from a genetic disorder, and they keep going from clinic to clinic without any hope until they came to his clinic, and he found that there is a treatment if they've been diagnosed earlier. But unfortunately, going to the medical genetic has a lot of obstacles. That's why clinicians don't yet apply it in their clinic. So it can increase the diagnostic rate. And for example, children who have some genetic disorder, if we can treat them and diagnose them very quickly, then they will have better life. So the stories coming today is from King Abdulaziz University, from our lab in the Center of Excellence in Genomic Medicine, from Genati Lab. We are a CAP accredited, so we are allowed to do genetic tests in the clinic. In our lab, we also do whole exome, and hopefully, some of our colleagues here already give an introduction. So whole exome sequencing is very useful in clinical practice because we're only targeting these exome regions that are responsible for about 85 of the Mendelian or genetic diseases. So diseases that we are sure there is genetic reason for them. So just also a quick recap of what is an exome. So an exome, okay, the pointer is not showing, but if we start from the left side, there is the human body. Inside the human body, there is the cell, and inside the nucleus, there is the DNA, that's long strand. The DNA consists, as much of you know, of long characters. So about 3 billion characters of bases are ACGT. And a region of these sequence can be a gene, and that sequence encode a protein. So a protein is an enzyme, is a hormone in your body. If something happened in that gene, a mutation or a missense or a frameshift mutation, sometimes it might lead to some disruption in the protein, and that can cause you a disease. So identifying and doing the genetic test will really help in the medical practice. But the question is how this can be happened. I mean, if you walked into the doctor office nowadays, you will still find they are using the same tools they're using 40 years ago. So we need to make them trust whatever we are doing and what bioinformatics and what AI, what HPC can do for them in order to make these technology work for real medical practice. So a typical medical practice for whole exome, it started with the patient. So the patient sent the biological sample to the lab, and ultimately the raw data will go to the clinical bioinformatics, and the clinical bioinformatics will use the HPC and AI tools in order to generate a candidate of mutation that is related to the genetic disorder he has or she has. Then the clinical or the clinician will use that to diagnose and provide a good treatment. But that is a typical workflow or scenario, but how to make it effective? Now, as many of our colleagues here, they talk, it's all research till now, and people keep generating more and more data without understanding its meaning. So the most important here thing is the time. So if a patient is in the ICU or he is in a condition that he needs immediate action, of course, the physician will not wait you for about a month or 2 months to tell him what is the cause. And not that only the problem, it's also the big data. So for the whole exome, which is an NGS technology, next generation sequencing technology, we know that it's a big data. And Prof. Mohammed has shown how big this data. I'm just gonna show you here that it is also from the analysis, also it's getting increased. So if the raw data is in terabyte, then we perform multiple analysis on this data. We do the alignment, we do the variant calling and the annotation. And in each step, we keep generating more and more data. So it's obviously, it's a time and space consuming. And let's say we solve the space by using high information technologies. But what about the time? Time is very crucial here. So in our lab, we try to do what we can do. In Lenovo, they done a great job by utilizing the hardware, and that is also valid. And we know in the market there are other also hardware that trying to accelerate the process. But also, if you are in the bioinformatics field, you will know that there are a lot of tools, there are a lot of packages, and which one is the best? Okay, which one will give you good result, accurate, good mapping, good variant calling, less false positive, and also a reasonable time. So for that, you need to do your benchmarking. So benchmarking and simulation analysis that we do with using of the HPC is providing us with a result that at least satisfy us for our current work. So there are two tools. So in our lab, we use the sequencer, NovaSeq. This sequencer generates about 20 patients per run. Okay, and again, one patient can go as a raw data for more than 7 gigabytes. We connected our sequencer to Aziz supercomputer directly with a secure channel, and all the data over the night migrate to the sequencer. And then we access, the clinical bioinformatics will access the data and will start the analysis. Now, as we want to do this, we want to make it much more usable for our physicians. First of all, we are using GATIC from Broder Institute, which is a well-known institute in the field. And GATIC has really trust in many for clinical use, and there is a best practice. But the time is here is a question. So what we do, we looked at a new technology called Dragon. It's similar to Lenovo. They're also using a programmable gate array, a hardware solution, but it is expensive, and of course it's need a lot of expertise. So we've been lucky that Dragon and GATIC have a collaboration, and they give us an open source code that we can utilize, and that's what we did. So here you can show the methodology we follow. So we took our best practice, the aligner that is recommended by GATIC, the BMA, and the hypertype caller, and we compare it to the new aligner, BWA MEM2, and the Dragon GATIC Spark enable. So, and simply what we did, we run the two pipelines on the same job array on Aziz, and we try to make them all equal in the number of node and CPU. And for the data set, we use a well-characterized sample called genome in a bottle. So we bought these samples, we run them in our lab, and we download the raw data, and we compare our data with the data of these samples. And also in our lab, because we maintain our own local database, we have also used some of real data, so real patient data with different sizes, because we want to reflect the routine, exactly what is going on when we have a real patient coming to our lab. So the result shows, of course, it's not compared to the number of hours because that is a hardware solution. It's more effective. This is just a software solution, but you can't see the performance comparison, for example, for the endl, which is an issue. So the endl is when you have a short insertion or a short deletion. Usually these are not very good. It has a lot of false positive. So you can see here in the previous best practice, it was 70%, but with our comparison, it goes to 94%, which is really, really great increase in the accuracy of the result. For the time and the performance of the time, you can see also there is for the aligner and for the Gatic caller, both of them showed really a good in the timing. So we save a lot of time. And this figure is showing you different samples with different size of their data. And also we show that in the aligner and in the caller, we are achieving a good time comparing to the previous practice. Now, what I'm talking, or the message that I want to deliver today is how to use the bioinformatics to bring the bioinformatics to the clinic. So first one was a benchmarking study trying to enhance the time. The second one that also done after the data analysis is the interpretation. So, okay, you have the variant, you have the VCF files, now what to do next? You need to rank them. Now this process is usually done manually, and many of the people in the field knows that they do this by searching the databases and trying to find a matching between the list of the variant and the relevant phenotype. Now, this genotype, phenotype, or variant interpretation, we done by using a priori algorithm. Now, I know this is a simple algorithm that everybody knows in AI, but here's the idea. In the clinical setting, you don't need to use a very sophisticated methods because at the end, there is a difference. So if you do a research-based tool, then it's about have you success? Have you found what you're supposed to find? This is it. But if you do your tool for clinical setting, then there is another questions will be asked, like, okay, you found that, what you missed, okay, or how you found it. Give me the interpretation. Why you say this is the cause of the disease? What is other things? So it's more like educational, not just by the results. So for that reason, we're using association rules. We apply it to all of our data, okay, and we try to find the rank of the variants in order to give it to the clinician by using AI automated tools. So the VCF file, we trained it by a priori. We created a knowledge database, and the recommender system at the end will enter in VCF file a new patient coming, and we will prioritize the variants in order to tell among the 40,000 variants generated which one is more probable to be related to the disorder or to the phenotype this patient has. Okay. So here I'm showing just a quick demo of the suggested tool. So this work is still under development.
هذا التطبيق عن استخدام بارتيونس هو عبارة عن ويب سايت
It's not showing, I think. فتح الفيديو لوحده. كيف تفتح هذا؟ It's okay. I think I can skip, no problem. So the idea of this tool is that it will be used in the clinical setting. So we need, as we said, to make it interpretable. So the clinician will upload, or the clinical bioinformatician will upload their files, and then there will be a list of variants based on the knowledge. So again, here also a promising thing to be said is to analyze the data in the real time. You can't just depend on building rules based on previous or history data. So for example, if I build a rule-based or a knowledge-based system for chemistry, then HO is something, it's a rule, it will never change even after hundreds of years. But for medicine, the practices change every day. So you can't just rely on history data from 20 years. You need to keep, as you enter new patients, you keep analyze them, you keep update your knowledge base, and that is the promising. That's what the clinician need, because it reflects exactly what's happening in the clinic. We can't just build a model and give it to them. We need to keep updating. So inshallah, this model will be inshallah published soon. And finally, because I know that I don't have much time, but the other side, which is the bioinformatics research, or what we called R&D, this is also we do. So we have lots of data. We are trying also to use public data in order to model some problems in biology, because this also can be used in the future. So I'll just give you an example of what things, other problems we can think about. So one of the example is the human clock, or the internal clock, which we call the circadian rhythm. So this internal clock is maintaining your temperature, your other things. And there is a theory saying if this clock's been disrupted, that will affect your health and ultimately will cause you with some chronic diseases such as diabetic and all of that. Now the question is that how do we know if your clock is disrupted? Okay, can we have your blood tested and I can say, okay, you are moving. So also this for enhancing the medical practice. So here are this figure showing you the gene behavior from day to night, the blue curve, when you are okay, when your circadian is not disrupted, and the red one is showing how shift is happening due to aging, to lifestyle, sleep pattern, and all of that. This is very useful if we say that, if you know that some of the medicine, for example, will become more effective if you use it in a certain time. So we will know by measuring your disruption when you are supposed to take this medicine and make it effective. For example, airplanes also might need to know if their pilot is disrupted, if they fly a long flight, are they okay? Because also disrupting the circadian rhythm might affect the mentality of the person. And of course, the shift work. We read a lot of publication that the nurses and all the shift work, they are suffering from cancers and other diseases. So we use in our lab, we have, in our center, we have molecular genetics scientists, and we form a mathematical model using two genes, NRD1 and NRD2, that's well known that they are stable. So whatever disruption happens, those only two genes will never change their behavior. So just to summarize, because I'm running out of time. So simply we use an anomaly detection method, anomaly detection to model all of the normal samples who have really not disrupted in their gene pattern. And then we measure how deviate the patient from this normal sample. So, we are being really lucky that we have show about 0.03 of the significant from the normal sample to the deprivation samples. And that model can be used. We are still working on to confirm it and validate it, but it's hopefully it will be used in the future to help in this identification of the disruption. So as a summary, in order to make our work and research in bioinformatics valid to our clinic, we need to think about the turnaround time. We need to explore and use AI model and the information technology with a wise way, because we don't want to make it complex. We want to make it easy, because the interpretation is very important in this field. Doctors will ask you why you come up with this result and how you come up with this result. And finally, the mathematical model and using some prior knowledge also will help to increase the efficiency and applying the bioinformatics and AI in medical settings. That was my time. Thank you so much.
For the interesting Now we will open the discussion and the audience question. You may have the QR code. Okay.
نروح اللي بعدها ولا هذه؟
Yes, you can scan the QR code to ask any question to our speakers. Until we receive your question, I want to ask Mr. Philip. It was an interesting presentation to know the exceptional features in the Axiom processor and GPU. So, what are soon to come features for the Axiom processor and GPU that can make difference for application in especially medical research?
Okay, thank you. As I said, the next Xeon processor codenamed Sapphire Rapids and the next GPU from Intel codenamed Tomography will embed a lot of accelerators, especially for the AI aspects. And as we all know, Intel only brings ingredients that our partners use to differentiate and provide a certain type of solutions. And we bring the basic instructions, typically in that case for the Sapphire Rapids and Montevideo, the matrix multiply extensions. Then we bring them directly into the libraries, and the applications make use of these libraries so that it facilitates the development of the applications, both for solutions like GATIC or solutions like TensorFlow or PyTorch.
Thank you, Mr. Philip. Mr. Dishan, you mentioned that the Novo Genomics optimization and scalability tool, or as you said, both, not require any accelerator on the GPUs. So does high bandwidth interconnect also have the same effect in the performance?
Yes, so the interconnect depends on many factors. One of the main factors is that if you have a job running across the nodes, then you require high bandwidth, but this is not the case in the Ghost. So the bandwidth that we require is to move the data from the centralized storage to the local storage, because that's very important. If you have the data on the local storage in the server, then you have better performance. So the interconnect will only be mostly be required only for the moving of the data in and out from the server, but not across the Ghost nodes. So ultimately, you might not going to find a very high interconnect as compared to the other HPC clusters, but a nominal interconnect will be sufficient.
Okay, so Genomics usually use the high or large size of data. So is it mandatory to have a high performance storage related to Ghost?
Yes, so in order to have a high performance, because genomics data generates a lot of data, terabytes of data. So the samples that you're running and when you want to run the jobs, that requires a high performance storage for sure. So yeah, there are two ways. Either you can run the data only on the shared storage and the nodes can communicate with. Or the second thing is that you move the data, as I mentioned, move the data internally. If you've seen my slides, we recommend at least to have 7 TB of all flash storage there in the nodes. So the high performance is required for that one. Yes, but when the result is there, then you can use kind of an archive storage to store the data because it's a big data. There's a lot of data that generates that one. So you can have a mixed match of storage there.
Thank you, Mr. Dishan. We can have a live question from the audience if they want to ask using the mic.
Well, I have a comment, not a question, so if you mind, if you don't mind. Well, we always, I really appreciate the papers really good papers, and I learned a lot today. Well, I'm Dr. Salman. Well, we always appreciate the results or the outcome of clinical AI engines. All these engines and all these products are based on a mathematical theory called graph theory. Graph theory has been used by mathematicians for ages, for a long time. But why didn't we use it for all this time, and why didn't we benefit from it as we see today in AI? The reason is the computer power that the manufacturers of processors are developing, because they developed so fast processors. We were able today to use these the graph theory, because it needs a lot of computer power. And if it wasn't for this product, which we normally don't appreciate, we only appreciate the end product. We don't realize that all this depends on this CPU or GPU, the development of what this gentleman using gave us the ability to use the graph theory, which gave us the ability to do better predictions and fast predictions on unrelated data. The difference between AI and other IT systems is the data are not related. It's not structured data. So we were able by graph theory to use this data and make meanings of that. And thank you for the manufacturers. We appreciate what they do that give us what we, results what we have today. Thank you very much.
Thank you.
Absolutely, as I said, and thank you very much for pointing that out. Moore's law has been extremely vivid in the past years, and we believe that it will carry on bringing additional computing power that is needed for graph theory or others. But as I showed on one of my slides, unfortunately, AI is requiring a lot more power and performance. And that's why we also need to get to something a little bit over what we are providing with just.
Thank you, Mr. Philip. We have a question to Dr. Mohammed Al-Arabi. Do you think that Kingdom will reach the databyte size of biodata on 2025, or will it be on later date for the next group?
I think this is a global scale. It's not related to the kingdom, but the problem here is the kingdom is if you don't have a very clear strategy for data sharing. You don't have a very clear methods on how we can exchange data. And sometimes it's very costly to reproduce the data or recompute the data. A lot of these biomedical data is very useful to actually use the produced results. So sometimes you really don't need to recompute it. Sometimes it's very costly to recompute it. So it's very smart to reuse some of these intermediate. The biological data has a problem of actually, it's totally different than these CFD kind of mathematical calculation or biological data tend to produce a lot of intermediate results. And in some clinical bioinformatics workflows, these intermediate results is also necessary for auditing. That whatever you're conducting is based on a standard and accredited. So I think the kingdom, we are not yet there. Zettabyte scale globally, we reach zettabyte scale, but in the kingdom we need to start somewhere.
Thank you. Actually, it was a very research that you showed us about analyzing images. So As we see, you got some patents for that. So my question is how you can enhance this product or what the future feature you are looking at.
I think my next move is I will say I want to straighten the chromosome and then also the one that I imagine secondly. But definitely because of the pattern, most of the part we can build the microscope because all the pieces of the microscope are there. We just need to assemble those pieces and install the software, and that can be commercialized.
Thank you, Dr. India. Dr. Noor, in your presentation, you mentioned that you are doing your research in your local data. So do you think we need to go beyond that, applying the model in national or international data?
Thank you so much for this question. It's very important because it's always in AI we ask how we analyze the data. So, for example, yes, we had it on our local database, but of course, the rule of thumb is the more is better. But on the same time, I also need to mention that it's not always the time. It's not always that the more is better because sometimes you need to understand the problem. If you add more data, you can make it worse. You make it more complex. If you heard about the Watson project, they lose a lot of money. They didn't receive any fund because they failed. They put all of the data, and then the model can't understand what is in the data. Now, this is also critical. I need a lot of multidisciplinary people to work together from the molecular genetics, from the medicine, from the computer science, all together to understand and to use the data in a clever way. Again, in medical settings, the result is not just about the success. It's about how you reach this result. It's more about the interpretation. That's why sometimes you will find linear regression, very simple methods works very well instead of doing, for example, deep learning, because these black boxes might not really help you to understand which features, one that is responsible. So it's very important thing to think about before we generate more data, because many researchers, when they start, they just generate more data, keep generating more data, and there is already enough data to search and about. So before we generate data and apply the same method, we will end up to nowhere. So we need to think differently now. Thank you.
Thank you, Dr. Noor. And in general, what is the biggest change you made to move to clinical bioinformatics?
Yeah, that is interesting because many of my students, they came and asked this question from computer science background, you shifted to bioinformatics, and then you shift to clinical bioinformatics. Clinical bioinformatics is what we call SOPs, validation. I never knew about this SOPs before, but people from the biotechnology and biomedical, they know this. So you need to do, your system should be very consistent. You should be validated. You can't just, for example, okay, this tool doesn't work, I will use this tool. You can't do this with a clinic. You have to be standardized and use really good practice in this sense.
Thank you, Dr. Noor. Also, I received a question to Dr. Philip. As you see, you say in the presentation that there is a merging between the CPU and GPU and give us a XPU. Is that published now, and is the processor is available as a project now?
We have announced the Controls XPU, I think, in March, in terms of the projects that we are working on and that we plan for around 2025. I think that Raja Kotebi, our EPGM of the AHG group, has announced 2024 plus. So in terms of general availability, I would report it for sometime 20. It's not very complete.
Thank you. Dr. Rekia, we received the question. Have you considered labeling the data within Automation? Yeah, labeling data and medical images can take it cost. So did you consider that?
Yes, I tried almost everything, but I got a decent result. What I know wasn't enough to go to the clinic. So eventually, I did the manual learning to work very well. I had to.
Thank you, Dr. Ilya. Mr. Mohammed, how HPC can contribute to solve the limitation in healthcare?
Well, actually, there is a very limited access in terms of academic institute to this HPC environment in order that at least primary research and clinical using clinical data. This is the first. Second is the availability for the clinical data that is accessible for people to analyze actually and to start to build models that can actually be used for the. So I think we're in the early stages. Now there is some cloud providers, and so the idea that will actually accelerate a little bit for this work. But in overall, we're still in a very early stage. I mean, we need to increase actually the relation between clinical setup and also bioinformatics or computer science colleges. We need to increase and create some very robust programs that actually can bring clinicians who actually be introduced to this bioinformatics workforce.
Thank you, Mr. Mohammed. We can open a live question. Anyone have a question? Yes.
Assalamu alaikum, shukran, Dr. Soya. Thank you very much for such a gathering. That's merges between computer science and medicine. I just have a question to the panelists. We've talked about the beauty of artificial intelligence in medicine and how it will help and how does it, what are the benefits. From your point of view, what are the pros and cons? Like, what are the challenges in artificial intelligence in medicine? Like when Dr. Bahari, it was a beautiful presentation when you clean the data many times, like many times. It was what are the challenges? What is the time consuming? To what extent we can clean the data in order for us to find real information without any false data? This is number one. The second question, what are the ethical challenges that we might face in artificial intelligence in medicine, like data breaching and cybersecurity? So we love to hear from you. Thank you very much again for organizing such an event.
Thank you.
I think so far, the only promise I can give is going to be not full automation, but suggested. I think that has to be clarified by the technologists. I don't think very soon it will be full automated, like just you put the sample and the abnormalities is going to be the physician immediately. It has to be verified. And about the labeling, yes, I think it was very difficult. I don't think if I wasn't working with such genetics, it would work because I can validate my results. Otherwise, it will be back and forth between search geneticist and artificial intelligence engineer. Usually, engineers get bored when they don't like the problem. They don't do more. They don't like to work with the problem that they don't understand, like analyzing the X-ray, analyzing the CT, MRI. It's boring for them. So if they don't see good result, they usually give up and try the problem that's familiar with pedestrian detection or those kind of problem that they're familiarized with. So I don't know if I answered the question.
Actually, regarding clinical data, I think the rule of thumb is to follow on this HIPAA compliance. So data encryption is really very crucial. And this actually had a very high cost to compute. Because handling clinical data, this is individual data. This is human individual sensitive data. So working with such data requires actually encryption in risk and wire transit. This is actually very important to look at, especially Hpc, as we have a really very high level of data compliance, and especially regarding the regime of the variables. And there is actually a regulation governing actually clinical data and actually using clinical data. And for actually the labeling of the data, and actually this is maybe sort of can actually add to this regarding the data itself.
So now you want to add about the labeling the data?
So for privacy also for data, it's very important. Now we're not allowed to contain clinical data from the patient. So yes, privacy, making sure that this raw data belongs to the right patient is also important. But considering AI, there's lots of disadvantages and advantages. So of course the advantages, you would automate, you would be having more good tools to speed the process. But the main thing in biology and in science is the discovery. So actually the ultimate thing we want AI to do, and that's why we need a genomic HPC, a genomic AI that deal more with interpretation and analysis and understanding of the problems. So this is what I can think about the advantage of AI, but the disadvantage, of course, is the disadvantage of AI. If you use it in the wrong way, it might lead to the bad results. So it's, I think AI is intelligent enough that we need to be wise with the ability.
Thank you, Dr.
Let me comment on something. So you mentioned about the challenges of HPC AI. That's very important. One of the challenges there is the power and because you have the technology available. And more and more research work you do, you require more and more computational power. And that is a challenge in every data center these days, the power and the cooling availabilities, because we need to have efficient data center. We need to design the HPC architecture very efficiently in order to do that. So you're going to see the processor, the GPUs, are going to keep on increasing the GDP values. So that's a big challenge that's coming up. So we need better technologies to cool down and stuff like a water cooling or something like that. And for the security, yes, that's very important because that's a very personal data and very secure data. That's why we in the HPC field, we won't, but especially for the biomedical research, we don't encourage to have some public cloud. We use public cloud for that, for those HPC, because there will be no privacy for that data. So in-house or maybe like a community between the universities or a strong a secure environment that you can have the data, that is more preferred, but also not the.
Actually, also one important aspect is now it's emerging is there is no data access to file system. Data are actually kept in data buckets that which is for the user with certain privilege. So the user cannot really manipulate the data on file system.
You raise an interesting question, which is all of the challenges. And the list of challenges on this is so long that we can spend days talking about it. And why is this the first session that we're talking about here? It's because people want to get a better world. It's a challenge, it's an opportunity. That's why it takes so many brains and so many bright people to achieve that. So it's, as I said earlier, it's only all together, the hardware, the software, the developers, the expertise on AI, on HPC, on medical clinics and stuff like that, that will get us that solution. It will take time, but we have the right brains to do that.
Thank you, Mr. Philip. As we reach the end of our session today, I would like to thank my speaker, Mr. Philip, Mr. Dejan, Dr. Novo Genomics, Mr. Mohammed Al-Harawi, and Dr. Yahya Bukhari. So thank you all, and I would like to thank the audience for their attendance. I would like to ask from Mr. Abdullah to answer this. So, Dr. Philip, Dr. Rashia Bukhari. Mr. Mohammed Al-Arawi. Mr. Dishan Kamal Siddiqui. Dr. Novo Al-Ghani.
العافية.
Okay, thank you, Dr. Asmaya, and all speakers for the interesting speech. And now we'll move to the next speech shared by Dr. Khalid Al-Isa. So Dr. Khalid and participants, please join us to the stage. This one is
السلام عليكم. بسم الله الرحمن الرحيم. Good morning, ladies and gentlemen. I would like to invite our esteemed and wonderful panelists to the stage. Professor Banda, Professor Rashid Mahmoud, Professor Muhammad Al-Shahrani, Dr. Saber Faqih, Engineer Ahmed Al-Jishi, and Engineer Saeed Zaman. Please.
شاشة ثانك يو شاشة ثانك يو في شير
It's an honor to welcome you all to this wonderful panel discussion today on HPC in healthcare. It's a pleasure to be a moderator for this panel with these wonderful and esteemed guests, which we will get to know, inshallah, in a few seconds. Today's sessions, I will ask our members to introduce themselves in a minute or so, and they will have a few questions. After that, we'll open the floor for questions from the audience. So if you have a question, write it down and get ready when we hand you the mic. I will start this session by introducing myself. My name is Khalid Isa, and I'm honored to be the moderator for this session today. I'm currently an assistant professor in the Digital Forensics and Cybersecurity program in the college, and also I'm the CIO, or the Dean for Information and Communication Technology in this university. I would like to ask our esteemed and wonderful panelist member to introduce themselves. We'll start with Professor Rashid.
Assalamu alaikum. I'm Rashid Mahmoud. I'm a professor in King Abdulaziz University. So we have a HPC center there. We have a supercomputer called Aziz. We manage it for the university. We provide research services, and I take care of the research side. So I'm the research director there as well.
Thank you, Professor. It's an honor to be with you in this panel. And now we'll move on to Professor Anna.
Hello, good morning. So I'm a professor at the Ohio State University in Columbus, Ohio, in the US. And my focus is mostly on the HPC, AI, machine learning, big data. So recently we have been working quite a lot on the healthcare kind of fields that I will talk.
Thank you so much, Professor. It's an honor to be with you on this panel. I will move on to our third guest, Professor Shahwani, if you can introduce us, please.
Assalamu alaikum. My name is Mohammed Shafani. I'm a professor of physical and medicine at University. I'm the hospital director here at Hospital University. Happy to be great panel and great audience.
Thank you, Professor Shahani. Our next speaker or guest is Dr. Sabir.
Assalamu alaikum warahmatullah. Sabir Al-Fatih, Senior Computational Scientist Team Lead at the Cost Supercomputing Product. And we take care of supercomputing users in our HPC infrastructure, from software to REST hardware and support, training, as well as educational programs.
Thank you, Doctor. And our next guest is Engineer Ahmed Al-Jishi from HPC.
Assalamu alaikum. My name is Ahmed Al-Jishi. As you can see, we have all number of Android HPC conference, as well as the region head for AI.
Thank you so much, Engineer. And last but not least, one of our most important guests, Engineer Saeed Zarwani.
Assalamu alaikum. I'm Saeed Zarwani, Chef of the HPC National Committee. I'm Senior Director of Cloud Engineering at newly established joint venture in Saudi Arabia called Conference. I'm glad to be part of this.
Thank you so much, Engineer. As you can see, ladies and gentlemen, we have such diverse panel and experts in this session. So hopefully it will be very, very informative. I want to start with Professor Shahwani, as a medical background, as a general director for such a huge hospital. My question is, what are the major challenges you are facing in healthcare?
Thank you. Yes, to answer this question, we have a lot of challenges, as everyone knows. One of the most important things, day and night, about uncertainty, even though difficult efforts. Department quality, patient safety, every hospital, our hospital, one of them, keep reporting like quarterly medical errors that happen differently in scale. However, when we analyze those medical errors, we found that most of the time is something that can be done, not done. The rest of this way, and the KPI to be built afterward is how can we do something about decrease the risk of this medical error. However, we don't find always, we cannot say eliminate the error, we're trying to do so. So always medical error is something that that's nice with every hospital. And we believe there is something getting more accuracy. And every error, when I say the errors are formed about patients, sometimes diagnostic times. So it's many aspects. So I'm sure AI can help a lot many aspects. One of the other challenges that you aware is resources, time resources, and especially about human resources, short staff. It's something that all the time being discussed. Bringing automation from these many aspects can help a lot the safety of this challenge.
for example, I'm saying like it can, you know, what which is like happening for CD per day, now logistics rates, and leave every position to be something cannot afford that. I mean, it's a challenge for radiologists. We need a lot of like AI and help and actually precise way of diagnosis. I can also tell about timing in various some interventions because sometimes time is not and the delay always be found that also having a lot of things by human manual staff. So making lots of things difficult fields might have very good time sensitive intervention that is done in correct and precise way and right.
So yeah, I can say one of the biggest problems, how to AI and HPC to do some common work that can be done with machines and use to more complex jobs. And I think also this will also help in reducing the mistakes and reducing the risk. This also reminds me of the story we heard in the first session about the three sisters who suffered because they were not diagnosed correctly early. That leads me to Professor Rashid. How can AI and HPC help in solving these issues?
Okay, so I just want to say something about the challenges as well before I talk about AI. So generally on high level, we can say that data is a challenge, data storage is a challenge, data processing is a challenge, and of course parallelization is a challenge, and also because data many times is not generated and in the center, so it's generated at the edge. So bringing the data to the cloud or code is a challenge. And therefore, we need to develop new methods which can act on the edge, where the data is generated. But these things can be done probably easily. Always adoption is more difficult by the user or by the community. So today it was discussed by Dr. Muhammad that the data federation that providing data available to people so that people can access the data and they can use the data in new ways and ask different questions. So creating that infrastructure, I think, is a bigger challenge. The adoption is a bigger challenge. So how AI can help? Naturally, AI, because AI is a kind of human intelligence, because we basically translate our intelligence into computational power, and that computational power, we kind of perfect it and we kind of accelerate it so that we can automate things and we can do much faster. So we know, there are experts here. I'm not expert, but generally we know we do image analysis, we do video analysis, we do textual analysis, we do numerical data analysis, and there are so many applications there. Image analysis, that we can diagnose diseases through voice, through images. We can do textual analysis to understand, for example, social networks, that what people are thinking, in terms of diseases. We have done this kind of work, both psychological and physical diseases. So, all these are, venues where AI can help. So, of course, it can help the computational infrastructure itself as well. The adoption itself can be solved by AI.
So you're saying we have the ability to do analysis and read the CT scans and the images instead of having doctors do this job. Why we are not applying it?
Okay, so one thing is that I'm not saying that we have reached to the pinnacle. Of course, we are developing it, but this will be developed. We are already much better, and the speed of adoption of AI to basically translate the human jobs
automate it and rather, create autonomous infrastructure which can actually proactively work on data and so on. So I think that challenge is being solved, and that will get better and better. I think it's not the pinnacle, but it will get better and better.
Thank you so much, Professor. I also believe one of the issues, Professor Panda, is that HPC and AI solutions are very expensive. And we know that because we're trying to adapt some of these solutions and they are very expensive. How can we justify the costs?
Yeah, I mean, that's a very nice question, and I think the community is facing that. The way I'd like to answer, everything, like when you come up with a new solution, the behavior is expensive. So, for example, like I'm working with some computational pathologists at Ohio State University. We have actually taken our deep learning training to real computational pathology images. Initially, they were taking like almost 30 hours to do the training, and using parallel computing, HPC, we have reduced to half an hour. So it's a 60 times improvement. But of course, I mean, somebody has to pay for that cluster to do the training. But the idea is that, I mean, if we can demonstrate those principles, look at the cost of the pathologists, at least in the US, they are so expensive. If a pathologist is spending 15 minutes, they are charging like $500 or $1,000 to do the analysis. And if we can reduce that to 4 minutes, you save the cost. So we have to balance the technological cost, and then it will get translated to real benefits.
So we have to show that these expensive technology will save time and save lives, and at the end it will save also money.
Yes.
Thank you so much, Professor. My next question is to Dr. Saad. As a lead researcher in the area of HPC and medical research, what do you think are the trends in research when it comes to HPC AI in healthcare?
Yeah, thanks for the question, and it's really relevant. And we've been working with these researchers over the years, and we've seen the development at multiple levels and different stages. And what we noticed is more and more convergence over time at multiple levels. So I start with the first level is a convergence in the infrastructure and hardware. So we start converging, for example, so we are lucky at CARS that we have what we call the supercomputing core labs. Those are a collection of 12 laboratories. And we started seeing synergies and more connections between the supercomputing lab with the genome sequencing lab, the bioscience lab, as well as the imaging and characterization that they have, the cryo-electronic microscopy. And they visualize proteins, and they get 3D reconstructed in our supercomputer, and then we link to our fourth lab, which is the BIS lab here present today, if you want to chat with them, to have a 3D immersive visualization of those proteins. So we've started seeing this convergence in infrastructure that enables new workflows, that enable scientists for faster discoveries. The second convergence would be in the multi-science, multi-domains. One is traditional HPC and AI that's happening more and more often. So the latest example is AlphaFold, for example, developed by Google, that is a problem that hasn't been solved until today with the help of AI and the large computational power that is provided, used for that. And then we started seeing more and more of these kind of multi-science disciplines working together to solve these problems. Another example is the natural language processing, the NLP in AI. This is an area that is initially tackling things like language and tweeters and social media and so on. But now they are using the same technology to look at genome sequence as a text. So we started seeing our bioscientists converging and working with these people to work on these kind of areas altogether. So yeah, so in summary, it's a trend of convergence that we started seeing at multiple levels.
Wonderful, thank you. Here you go, our researchers and professors in the university. If you want to funded research. These are the topics that inshallah comes to fund you. My next question to my guest, is Zabani. As you come from large industrial institutes in the kingdom, Aramco, Saudi Aramco, what do you have recommendation to maximize the impact of the HPC AI conference to bridge the gap between government, academia, and the sector?
Thank you, Dr. Khalid. For those who know me, I've been in the conference since in the early days. So, thank you. We have a good story. So I believe we will have a good story to tell because since 2011 we have been growing in the community, the HPC community, and I'm glad actually to see this growth year after year after year. One of the recommendations, if I would recommend something that we need to focus more on, is to invest in human resources. The biggest challenge I believe in the future is to educate and to basically to provide these young generation with the right knowledge so they live in the future. For the past 2 years, we've been trying to include things that can increase that competency. One of them basically is adding the hackathon, allowing students to present sessions here. And unfortunately, in the past 3 sessions, we're not able to do this. Thanks to Dr. and his team for their support this year. We have the first hackathon hosted at the university, and I think this is a great achievement. So if there's one thing that I would recommend to focus more on, to increase the collaborations, to focus on the human part, that's be it the students, in this case, the educators also, because the educators, they will enrich the user experience, and also the professionals, in that respect. One key thing maybe we'll see it tomorrow, hopefully, is to allow more students to participate. I think this is a good venue for the students to participate, share their experience. It's true that we should be aiming for quality, but at the same time, this is a good venue for different students from different organizations, be it whether students or professionals, to share their experience, socialize with with colleagues from government or academia or industry.
Wonderful, thank you. So I agree with you. Human resources is very important. So I think it was a good step here at the university when we started the Bachelor of AI a few years ago. So inshallah we'll have more graduates specialized in AI. My last question to Ahmed Al-Jishi as a board in the Saudi HPC, people are asking what are the activities and events that Saudi HPC is planning for community in the region?
So thank you very much. Before I go into the question, actually last week, 2 weeks ago, I was deployed there. I passed by the so there was only a couple of people from virtual hospital, and they told me that we have this great challenge that there's thousands and thousands of protocols for breast cancer treatment. And basically, they don't have the time and the resources to analyze those. So what they did, they joined to work with SEDACA, which is what Saudi, which is our Saudi Data and Artificial Intelligence Authority, led by Dr. Yasser, and that basically is they work on the images they annotated them, they built up a system, they trained that system, and that system now basically detects whether it is there is a tumor or not. Okay, and it sorts all the mammograms by either priority 1, which means it is suspicious, or priority 0, which is normal. So the radiologist of the mammogram comes to analyze. What he does, what she does, she puts on only the highest priority, and then they go to the lower priority. This way, they detect the unfortunate cases of cancer much more fast because it's certified. What is more amazing is that the next phase is detect whether it's benign or benign tumor. So they will arrange it and sort it, classify it, and give it to the radiologist by sorting. And then the radiologist will spend the most important time on the high suspicious cases. And the next phase, they can go, and usually this cases is like cases like 5 or 10 cases per day or something like that.
It is available now.
It is available. It is working. It is developed. It's piloted in the virtual hospital. If you hear about virtual hospital, it's piloted there, and it will be deployed when successful to all.
Did they mention what is the accuracy rate?
Yeah, I asked them. It's nice. So,
Something.
Yeah,
I think that's one of the achievements. They asked the people around the project.
So back to your questions of the point. As for my previous recognition as well, we are focusing on the innovation. We started focusing on at the beginning. The conference was focused on the serious models and surgeons process. Then we started years ago to have a practice students doing courses. And this year we used the hackathon. So we want to increase this awareness within the students and even the medical students, which is the topic of this conference. The last we didn't reach out. So our conference now is focused on reaching out to those guys. So the genome project, the genome analysis. In the past 50 years, a lot of papers on genomes. Now, starting 2 or 3 years ago, we started with that. So this is the conference agent that is towards helping not only the typical users, it's the ability to have awareness like oil and gas, the researchers, but also we have the medical care and AI. 4 years ago, we changed the HPC from HPC and it was HPC Saudi Arabia to HPC and access. So it's we are, I hope we are in that direction, but we have advice to us, anyone in the audience is for
You're definitely in the right direction. Your organization can help a lot in awareness of HPC and now AI also. Thank you so much for everyone in your team. Would like to open the floor for questions from the audience. If you have a question, just raise your hand. Any question? We have a question there. If you can please state your name and the person you want to ask and what's the question. Thank
you. So I would refer back to this morning session where we see that in order to support healthcare, we have a constitutional system, we have a government framework, a software development. So since there are some similarities with traditional system, but there are differences. I would like to have your feedback that how is the future cybersecurity landscape specifically for HPC?
Okay. Who's this question that you
Anyone
who would like to answer? Professor? Okay. The question is, how do you see the cybersecurity landscape in the future with all the advances of HPC and AI?
Yeah, I mean, thanks for that question. That is actually a big challenge. I think there's a lot of work still needs to be done because
Just like, I think we integrated virtual hospital everywhere, like we are trying to deploy this system. So security is a big risk. So we may need to come up with like kind of there's a lot of research going on. I mean, still solutions are not completely available in the cybersecurity area. Different kind of encoding, different kinds of protocols to really make sure that because here we are dealing with a lot of real data, sometimes patient data, so we need to make the system completely secure to make sure that these systems become real practical.
I think that's a big concern. I may add, I mean, in our infrastructure, one of the major concerns ethics about, so we have a whole committee at CAUST about ethics on conducting research, especially when it comes to human data. And yeah, I mean, one of the prerequisite requirements for that is to have all the data, all human data in encrypted storages. So that's one prerequisite. So all the data has to be encrypted. That adds one layer of security, and even if we are breached, still the data will not be available for the hackers. The other aspect I want to mention is the fact that security is becoming more and more concerns worldwide, right? So not only for HPC, I mean, even more importantly for cloud and shared environment. And that is pushing even chip manufacturers like Intel and others, I can mention more about it, to embed more features of security within the chip itself. So hopefully, I mean, Professor Panda mentioned it, it's a long way to go, but there is a lot of awareness within at all the levels of the stack, from the hardware to the software to the cloud and providers of the infrastructure about these issues, and there are measures starting being taken to move that direction. I think the issue is when everyone has access to HPC and quantum computing and so on, this high performance computing, even most of our encryptions would be useless. They don't break it easily. Any other question? Yes, you can give them the mic, please. You can state your name and the questions you want and the questions.
I'm Dr. Shaykh, so I have a question for the whole board. So as we saw today, we are watching the state of all automation using AI. So I was wondering how we will deal with the things such as program bias, where the AI will give certain advantages to system groups.
I think the question is how can we deal with, if we reach full automation, how can we deal with
Program bias, yeah.
Program bias, where the program can give bias results.
It all comes back to the education, and basically trying to automate activities there by doing more work, actually scientific work in this area.
Yeah, so again, just like the security we discussed in the previous question, bias is also very important thing. It again goes back to the data. If you have really data from all different fields or whatever you are working on, there's enough data, then we can handle the bias properly. If we don't have data, then we take some amount of data and then make an algorithm out of it, and then you will not be able to really analyze it. So that's why I think in any field where AI is being used now, there's a lot of focus on increasing the data size so that we can train over a lot of different data. So hopefully that will help with the bias, but it's still an open challenge, just like in the previous question we said, it will still take some several years for these things to be resolved. So this is a very good research area at this point.
Enough data, enough training.
Yes,
that's the research.
Yeah, actually, I was about to add to that. If you look at AI in general, it's not only the bias, there are so many other aspects of AI. And it's a huge research area. Many global organizations, Microsoft, and others,
are basically doing this a lot, and there are many top-notch universities doing research in AI. And if you go just to research papers of Google AI, there are many books, very good books, okay, that talks about AI and how to handle the bias. Having, for example, that some programs were biased toward white people against black people, having that was biased toward all people against teenagers, girls against married people. We've seen all of those. For example, credit loans. Okay, they were biased toward certain race against another. And that triggered all this research around ethical AI. And thank you for the question. It's a very important research area. And I'll be glad to join that research and get us something around that. Thank you.
So, I mean, the AI risks, there are a number of things. So, for example, interpretability and explainability is one problem. I will come to bias, but I just want to give a overview. So, how do you interpret the models are very important because the AI models normally are developed for performance reasons and bias or any other things which can be there normally are not looked at. So interpretability and explainability is important. Then of course bias is important. Transparency, trustworthiness is important, and all these are risks. What is happening with data is that because naturally data comes from wherever it can come from, and the bias can happen because of, for example, social classes as well, that poor people don't get to be tested as much as rich people. It is possible. And similarly, the other social classes. So what they are doing is that they are, for example, FDA in US, they are looking into it. They are trying to ensure that the data comes from all segments of the society. But this problem is the same problem as for humans. We understand what is ethics and we understand what is fairness, but the society is not fair. And same thing will translate into AI models as well. And in AI models, the dangerous thing is that because AI optimizes things, so therefore it will amplify very quickly. And of course, governments have to put time into it to make sure that it doesn't happen. And also people's jobs will be taken as well. Once any job sector is in danger, then people will stop working in that area and then AI will take over. Once the AI will take over, then it is difficult to look into how AI is affecting the society because there are no people working in that area. So these all things are there. I think governments need to take action.
I think that's a bigger question. Is program able to be biased, or is it the data we need to program biased?
Yeah, in fact, if you take a step back, in current society, forget about AI, even the humans, bias problem is not solved. We have conscious bias, we have unconscious bias. So unless we solve that first, it's very difficult to take it to the AI level. So I think first this problem needs to be solved, and then we can translate that into other forms.
So we are somehow affecting applications.
Yes. Because we are designing that, and we have not solved that problem. And how would we expect the AI systems to be solving the bias problem?
Thank you so much. I would like to thank the audience for being here, and also would like to thank our panel member. Before we leave, I would like to invite the panel leader to give a certificate to our esteemed panel members. Thank you so much for being here. Thank you for sharing this information with us and giving us more information. Professor Khalid. Thank you. Professor Shemali.
Thank you.
Dr. Sabir. Professor Mahmoud. Did you think about that? بصورة خاصة لدينا الجنين عند الراني Thank you all for being here. يعطيك العافية شكرا جزيلا. Thank you for being here. Thank you for our team and talents. Thanks so much. Okay, we'll have to break now and we'll be back to close time, inshallah. Thank you so much. Prayer bless.
الله يعطيك. أنا من اليوم شغل بس الصوت أنا لأنه الستريم هذا المفروض أي الآن شغال هو. واللي هنا كم دكتورة؟ اللي هنا كم راح يكون؟
يعني 5
ما أتوقع لازم تشاء. الله يعافيك. بس ما يعرف. خلينا هنا.
اي الوقت تبتدي 12.
تمام انت طيب.
Hi, Professor Uthman, how are you? Inshallah, we will start in after 15 minutes. I think we are all set.
Yeah.
We can see your picture. Everything is
Yes.
clear?
Yes.
So,
Can you hear me?
Yes, we can hear you loud and clear.
Yeah, I just wanted to see if I can share my screen.
Yes, please go ahead.
I think someone else is sharing.
I will
So
see.
maybe-
You will stop our sharing and then you will see.
Yeah.
Try now.
Oh. Yeah, so let me just give me 1 second, please.
Okay.
Can you see it, please?
Yes. Yes, we see it.
So, okay, thank you. I will just quit.
Yeah, so Professor Uthman, it will be a 15-minute session, and we have another speaker. If something goes wrong, like a connection problem with him, so then we will send you a message that you can continue. You can take 5 minutes more if needed.
No problem. No problem.
Thank you much. We really miss you. We wish that we could have host you, but unfortunately, really, I'm Professor Nasrullah, and really, we are, inshallah, some other day we would like to bother you.
Inshallah. 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 We are very, very close to
Exactly. This was
1 hour. Yeah. Okay, inshallah. Inshallah. Salam alaikum.
Welcome. Thank you. Assalamu alaikum.
Yeah, salam.
اوكي دكتور انا جرب الحين تعمل معنا.
السلام عليكم دكتور عثمان.
وعليكم السلام.
حياك الله دكتور، بس نبغى نتاكد ان الصوت واصل. ان شاء الله we will start our session soon.
إن شاء الله no problem.
Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone to the second session of HPC conference under the title High Performance Computing in Artificial Intelligence and Big Data. Nowadays, with the persistent growth in data, high performance computing became a crucial solution to satisfy computing requirements for many AI, big data processing, and data analytics applications. In this session, we will be provided with a closer insight to the latest advances in high performance computing and artificial intelligence field, exascale and its challenges, and leveraging high performance computer for different sectors. This session will be provided as two parts, and we will allocate the last 20 minutes of each session for open discussion and audience questions. So please, if you have any questions for any of these speakers, you might scan the answers QR code and submit your questions via Slido. So now please join me to welcome our esteemed speakers for the first part of session 2. We have with us today Dr. Uthman Bouhaili. Dr. Uthman is the Director of Research Computing and Research Professor at Texas A&M University at Qatar. We have also with us Dr. Paul Kalikha. Dr. Paul Kalikha is the Director of the Cambridge Open Exascale Lab and Research Computing Services at the University of Cambridge. Both Dr. Uthman and Dr. Paul will be joining us online via Zoom. We have also with us Mr. Andy Grant. He is a Group VP, Large Strategic High Performance Projects at Atos Company. Mr. Andy, if you are here, you may join us on stage, please. We have also Mr. Sven Brunner, a Field CTO International at Vast Data. Welcome, Mr. Sven. You may join on stage. Also, we have with us Mr. Badr Badghish, a geophysicist from Saudi Aramco Company. Welcome, Mr. Badr. You may join us on stage. Also, Mr. Paul Brook will join us online. He is Europe, Middle East, and Africa Director Data-Centric Workloads Specialist at Dell Technologies. So please welcome our speakers for the first session for today. So we will start with our first keynote session with Dr. Uthman Bouhaili. Modeling in medical physics and nuclear medicine has witnessed significant increase. In the first keynote session, Dr. Uthman Bouhaili will tell us more about the ongoing research in area of radiotherapy and dosimetry. He will highlight the effect of multiple tools coupled with high performance computing sources and methods in medical imaging and welcome. I'm looking forward for your contribution to this conference. Yes,
Hello? Can you hear me?
Yes, we can hear you.
Okay, can I start?
Yes, please. Thank you.
Okay. Good afternoon. Assalamu alaikum. Thank you very much for this invitation and also for this opportunity. I also would like to thank the HPC group at Saudi Arabia, who is doing a great work locally and globally. I have very good friends from the team there. So my name is Uthman Bouhaili. I'm research professor and director of research computing at Texas A&M University in Qatar. Texas A&M University is one of the branch campuses that were established exactly 20 years ago, and we belong to the Texas A&M College Station in US. So what I will be talking a little bit today is I will give some case studies specifically about my research group in and high performance computing in medical physics by targeting two areas: positron emission tomography for imaging and radiation therapy for treatment of cancer and other diseases. So let me just give you an overview about research computing. Research computing here that I'm managing providing services to almost the whole country in terms of high performance computing software, scientific software, and support. So as you can see, we are growing very, very slowly. And the main machine now that we are using is called RAD2, and it is around 120 teraflops machine. So most of the work that I will be showing was done in this machine. So let me start a little bit about the medical physics, because this will be the main topic of my presentation. So medical physics is a branch of applied physics that deals with the prevention, diagnosis, treatment of diseases using physics principles, and it includes several subfields, including radiation oncology, medical imaging, nuclear medicine, radiation protection, and other things. So, for example, for the medical imaging techniques, we all know X-rays, ultrasound, CT, MRI, and positron emission tomography. And for the treatment techniques, we all know radiation therapy, which could be either conventional photon therapy, where you use photons to kill cancer cells, or you can also use protons, and in general, ion beam therapy, which use ions like carbon ions. There is also radionuclide therapy, where you use an internal source, radioactive source, or radioactive element that will be injected to the patient to kill the tumor or to kill the disease. And there is also another field, the theranostic, where the same radiotracer is used for imaging and for diagnosis. So if you look at the artificial intelligence in medical physics, it has been exploded in the past few years, and you can see just in the last few years, it has increased the number of publications and papers in medical physics that deals with AI is booming. And this is, as you know, because of larger data set available, algorithm development, and also because of the computing power increase. And this is also done in order to reduce the burden on the caregivers and nurses and doctors. So this is also a plot where you can see the many collaborative effort in artificial intelligence and medical physics. We have activities in Qatar, in Saudi Arabia, in other countries in the Gulf, but we still need we still have a lot of homework to do to increase our visibility. So the ongoing activities in my team includes imaging and therapy. I will be talking today about image reconstruction and imaging in positron emission tomography, and also dose optimization and radiation therapy. Let me first talk a little bit about the principle of positron emission tomography. Positron emission tomography is an imaging technique that is based on the principle of electron and positron annihilation. So we all know the electron, and the positron is a particle that has the same properties as the electron, except that it has a positive charge. So what happens is that when the electron collide or emit the positron, they disappear, they annihilate, and they produce two photons. And those two photons, they have exactly the same energy, 511 keV. And those photons are emitted with the 180 degrees in between them, so which means in opposite directions. How do we use this in positron emission tomography? So the idea is to inject a radio tracer that emits, so it's a an element that emits those positrons. You inject them to the patient. So the patient, the tumor is very hungry, it will eat those radio tracers, which are most of the time coupled with the sugar, for example. And the cancer cells are very hungry. They will eat a lot of this radio tracer. There will be a high composition of positrons that are emitted. Those positrons will annihilate with the electrons of the tumor, and then they will emit photons. So you can see the photon will be emitted, the two photons will be emitted in coincidence with 180 degrees. And the red line that you see here, we call it the line of response. So the number of photons coming from this line of response is proportional to the radio tracer distribution, which means proportional to the amount of sugar that has been consumed by this area. If the amount of sugar is consumed in an abnormal way, this means that there is a problem in this area. There might be a tumor cells growing. So how do we do this? We build scanners. Those scanners are equipped with what we call a block of scintillation crystals. You can see them here. Those are scintillation crystal. A crystal is a material that will detect this photon and will convert to another visible photon that can produce electricity, electric current, and this electric current can be read out by the computer or by electronic scan computer, and we can do a sophisticated image reconstruction to have a map of the body. And you can see in the computer, we see some hotspots, which means those hotspots are those regions of the body that are eating abnormal concentrations of radio tracer, which means those regions are not normal. They are not normal cells. So application, there are many applications of positron emission tomography, cardiac imaging, neuroimaging, oncology, and so on. So what we are doing mostly is the optimization of crystals and the image reconstruction, because this is a very, very hot topic, is image reconstruction, because the image reconstruction is the one that will give us the localization of the tumor. So this requires extensive high-performance computing modeling and also AI-based optimization. This is what we are doing. So what we do is we build the complete scanner via simulation, and we try to optimize those scanners. So this is just to give you some of the platform that we developed together with other collaborators. You can see the crystals here, and we were also have been able to model most of the positron emission tomography scanners that are in hospitals that are in the market now, and also those who are used in animal studies. So you can see some of the scanners that we modeled, the experimental measurements and our simulation, which are matching quite good. So, for example, this has been published almost 3 or 4 years ago. We can also place phantoms and optimize the scanner and the crystals with the simulation. Obviously, this requires a lot of high-performance computing. We are talking about a process that simulates the radio tracer, simulates the emission of positrons, the annihilation of electron positron, and also simulates the light propagation into the crystals and the whole electronics and signal processing. So in addition to that, we are also involved in a lot of AI in PET imaging, because as you can see, one of the goals of positron emission tomography is to identify the cell or the tumor with great accuracy. Now, the spatial resolution is a limiting factor in positron emission tomography because it depends on the crystal size. We need to have a crystal size that is large enough to absorb the photon, to detect the photon. But if you choose larger crystals, this means that you lose spatial resolution, you lose accuracy. So what is happening here is that if you have a large crystal, you don't know where exactly is the photon hitting the crystal. This is what we call the depth of interaction. We cannot know by great accuracy the depth of interaction. And I am giving you here an example. So let's assume this small red point. This is where the tumor is existing, and this is where the photon and the electron and the proton and the positron annihilate. However, we don't know exactly where exactly in this crystal the photon will interact. If we do a small mistake, what will happen is instead of taking the true position or calculating the true position of the annihilation, which will give us the true position of the tumor, we might do a mistake and do another reconstruction and do something wrong. So wrong estimation. So how we do? We need to know this depth of interaction with great accuracy. So the only way to do it is to combine experimental measurement, large-scale Monte Carlo simulation, and to train those models based on data and Monte Carlo. So how do we do this? We take a crystal experimentally, we scan those crystals with a pencil beam, we collect the light distribution for each position. We generate this data set. Those data sets will be given to a convolutional neural network program or algorithm, sorry, that will give us the DOI localization inside the crystal. And we use this information, this trained algorithm, in reality, so in the real scanner. Now you can see when we do this, we have a very good improvement. You can see that the localization of the tumor goes from 0.76 millimeters to 0.38 when we go to CNN, convolutional neural network. Not only that, but the accuracy is 99%, and also it solves the problem of the edge. You know, at the edge of the crystal, we lose some of the light because of the edge. So with classical algorithms, you get 50% of the accuracy, but with CNN models, we get 99%, which is a very, very good result. So this is one thing. The other thing, in normal PET scanners, we only detect the normal PET scanners, they have a length of 30 centimeters. We only detect 1 or 2% of the radiation that is injected into the body. However, in many cases, we want to do multiple scans of the body because especially in case of metastasis cancer, where you need to know exactly where are the tumor locations, different places. So the idea here is to go for a total body positron emission tomography. We call it total body PET. So here again, we have been very active in the last 6-7 years with our collaborators. And we built, in the simulation, of course, many positron emission tomography scanners. Not only that, but we also proposed some adaptive design. So the idea here is, unfortunately, in the past few years, we start seeing a lot of children having brain tumors and other tumors. You need to scan them, but you cannot use these big scanners because you lose accuracy. So what we are proposing is to have an adaptive design that can shrink for children and can increase for obese people or pregnant women, etc. So how do we do this? But remember, when you increase the size of the crystals, you increase the size of the complexity of image reconstruction, but you also increase the cost. So what we are doing here is we are trying to propose what we call a checkerboard design, where instead of filling the whole cluster, the whole crystal, the whole scanner with crystals, we do a checkerboard, one on, one off, one on. This reduced the cost by 50%, and we have been able to demonstrate that the sensitivity is not lost if we go for AI. Those are some very, very confidential results that we have. Actually, we are presenting them tomorrow in Edinburgh conference. One of my team members is presenting them tomorrow. And not only that, but the reconstruction is huge. If you remember, we are talking about 1 to 1.5 meters scanner. We will have billions of annihilation, and this will require a lot of reconstruction. And we are proposing to reduce the background using some deep learning, and also to cope with this large number of reconstructions using CNN models. So this is for to give you an idea about the total body PET on the PET scanners and how we are using AI and HPC to improve this design. And the good thing is that we can, thanks to the simulation and the validation, we can propose new scanners before going to physically build them, which is quite expensive. A total body PET scanner, it's around now $8 million. So it's very, very expensive. Then for radiation therapy, so I talked about imaging, not about an example of radiation therapy, is the radiation therapy used X-rays, gamma rays to kill cancers. Of course, there is also proton ion beam therapy that I will not talk about now. So the idea is to use linear accelerators to produce photons with appropriate energy, and HPC helps us in simulating this, but also AI, as I will say. So the main goal of radiation therapy is to kill tumor, but the main drawback is the dose. So we need to improve the dose delivery for patients. So the idea here is to give just the right dose for the targeted region, the region of interest, and also to minimize the dose for the organ at risk. So I will give you an idea here. So in the last 10 years, there has been significant statistical studies that unfortunately women who got treated with radiation therapy for the breast cancer, especially for the left breast cancer, depending on the dose that reached the heart, 30% of those women, after 5 to 10 years, they developed cardiovascular disease. I have a big group working in this with simulation and biologists in this. I'm not presenting this, but I just tell you that it's very important to manage the dose. So 30% of women who got treated, they develop after 5 to 10 years cardiovascular disease. So those are real proven statistical studies that has been published in the last 10 years. So the idea is to minimize this dose. So that's why we are doing a complete modeling of linear accelerators and Linux in clinical Linux. You can see here some of the models that we have been working on. We produce, we simulate the target. So the electrons, they will hit the target, and with the Bremsstrahlung, they will go, they will produce photons, and those photons are the ones that are used in conventional therapy. And then we simulate everything, the flattening filter and all this. And then we can simulate the phantom or also the human body. So here we simulate everything that is involved, all physics processes from photoelectric content to Rayleigh scattering. And we are interested to look at the two important parameters, the dose distribution along the beam and perpendicular to the beam, because this is really what the oncologist and the medical physicist in the clinic, they use to deliver the right dose to the patients. So you can see these two, the dose that is perpendicular, the dose distribution that is perpendicular to the beam and parallel to the beam. This is our simulation compared to the experimental measurement that we have measured in a water phantom, and you can see they agree quite well. Now we are doing the same, but with human phantoms. Okay, so in addition to that, thanks to this simulation, high performance computing, and also AI, we have been also asked by a hospital to look at the staff safety, especially in the CT, for example. When you have a CT like this one, the CT cone CT, you can easily get some radiation going to the staff members who are administering or taking those imaging set. So what we did is we simulated, as you can see here, the full CT scan here, a CT device, and we placed also some 4 detectors in the CT room, and we were able to identify the hotspot and to deliver a 3D model and 3D image of where are the hotspots in the room, in the imaging room, that nurses should avoid. So this is just one area of where we applied high performance computing, especially from the scattered rays, because those photons, they scatter, they don't go into the patient, they go into the phantom, but they scatter. And when they scatter, they are deflected, and then they go to places outside the area of the couch. Another thing that we are investigating is reducing the dose in CT. Now, when you have a patient who has cancer, this patient unfortunately has to go through different CT scans, but the CT is photons, is radiation. So the idea is to reduce, and we have now in the literature clear evidence that doctors start worrying about the amount of radiation that goes into the patient from the CT scans. So one of the ideas here is, what if, so the goal is to reduce the dose. Everything is here is to reduce the dose. That is the goal. So the idea is, what if we go and start taking low dose CT scans, okay, and train a model that from these low CT scans, we generate a high resolution image. This is an ongoing work, and this is also something that we are doing for the PET, because the PET is, we are talking about 140 megabecquerel. It's a huge amount of radiation. So this is one thing. So what I talked about is imaging radiotherapy. Now I'm going to present some few slides about one of the groups here. It's not my work, but those are my collaborators who also use some AI tools to produce an application to predict the score of diabetes for Qatari population. So they used a database now I think it's more than 8,000 patients, where they built a neural network application. And this application now you can download it on the mobile, and you can just fill in 5 or 6 information like the BMI, the waist diameter, and some of other questions. And then they produce an application, and this application will give you the score and the prediction for the next 10 years, the probability that you might get diabetes, type 2 diabetes. And this application now has been in test in 2 hospitals in Doha, actually in Qatar. The last slide is one of my collaborators also is using AI guide aesthetic surgery with the surgeons from here, from Sidra and Cornell Medical College, where they are trying to help the surgeon to reconstruct the face, especially in the cleft lip syndrome and the Treacher-Collins syndrome, where the surgeon needs this AI guidance to do the surgery. So that just want to give you an idea of what is being done here. Yeah, so as a summary, of course, medical physics is a very, very fertile field for AI, but it needs also a lot of high performance computing. We are working on image reconstruction, but also the most important thing for us is to reduce the dose. This is whenever you talk to a doctor, he will tell you, I want precision planning, but also dose optimization. And by combining data and Monte Carlo modeling and AI, we can do this, as we have already proven some of the in some of the work that I showed. So thank you very much, and I will be happy to discuss and collaborate with whenever for anyone who is interested. Thank you very much.
We will get back to you at the end of this session for discussion and audience. Thank you very much. So talking about high performance computing, we does talk about exascale. So the second talk will be with Mr. Andy Brand from Atos. He will provide us with a presentation about role to exascale and how exascale computing machine as a transition of high performance computing towards exascale.
Okay, great. Thank you very much. And yes, so I'm head of HPC AI and quantum sales for Atos, Atos being Europe's leading supplier of HPC systems and one of the leading vendors worldwide for high-end computing. So I'm going to talk about the road to exascale. To some extent, we've been on this journey for a long while. It's taken roughly a decade or so since the petascale barrier was broken. The exascale barrier was broken earlier this year, or publicly announced, with the Frontier supercomputer in the US. Other parts of the world are now implementing their exascale strategies, in particular Europe, India, Japan all have, and UK all have paths to exascale. So what does it mean exactly, and what's our strategy for exascale? Well, of course, higher performance is one thing. Clearly Clearly, these systems will appear in the top 500. Top 500 is politically quite important for a number of customers. It's a flag to wave often, but really more important is the scientific capability that exascale platforms will deliver. For us, and a core part of our strategy is how we can do this in an energy efficient way, particularly with increasing energy prices around the world. Having energy efficient systems and lowering the carbon footprint to get to exascale is vitally important. And then the third thing is around sovereignty and making sure that we develop sovereign capabilities for whatever geography to make sure that we don't have supply chain dependencies that can impede on the ability to deliver exascale. So our platforms, and the picture here is for our new platform, which we'll be announcing at Supercomputing in a couple of months' time, called Sequana XH3000. But this is a hybrid accelerated supercomputer. Hybrid, mixing the capability to perform AI as well as HPC, but also the ability to mix on premises with cloud-based solutions as well. And a key part of this is around AI optimization for the system. So not just using the system to deploy AI for other things, but building AI into the system to optimize the system itself. So on the energy efficiency topic, if we look at today's technology and try to build an exascale system now, it's roughly 600 plus racks, 56 megawatts of power to do that. Very expensive in terms of not just capital costs, but running costs as well. By this time, over the next couple of years, with the newer generations of CPUs and GPUs coming along in those timescales, we expect to be able to build that exascale system in about 120 racks and with less than 20 megawatts of power. This is the threshold that we've set ourselves to do that. Just click ahead here. So you can do it in, obviously you can just add more and more compute, and this is not a very intelligent way of building exascale platforms. To get 1,000 more floating point operations, takes a lot more additional energy, so it's not particularly energy efficient. The better way is to look at how you can optimize a solution, fewer wasted flops with less hardware than your carbon footprint from the production of the system, as well as the running of the system, using intelligent software to drive that, ultimately driving fewer watts and improving the overall time to solution, and consequent energy and cost savings that come from that. So what do we mean by building intelligence into the system? Well, first of all, here's an example from one of our customers, which is ECMWF, so the European Centre for Medium Range Weather Forecast. Perhaps I should have used a medical example, but this is a good one to explain the point. In this particular case, their weather forecast model, called IFS, Integrated Forecast Model, roughly takes 1,000 seconds before this particular optimization. 30% of that was on the physical processes that needed in this weather forecast model. Of that 300 seconds, by replacing the physical kernel or the computational kernel of that code with a neural network running on GPUs, we were able to get that down to 4 seconds using a software toolkit that we have called AI for Sim, AI for simulation. So 75 times reduction on that core component, leading to an overall 30% performance gain on this particular model. So that's an example of using integrated HPC and AI in a particular weather forecast model to get improved performance and reduce the amount of time needed to get to solution. But how do you do it then for the machine itself? How will AI drive the supercomputers themselves, or the design of the supercomputers? And we think AI will effectively be everywhere in the systems. So in our new platforms, we're using AI software integrated into machines to do predictive maintenance. So try and look at fault patterns as they're emerging to predict when components are going to fail before they actually fail, so that we can do proactive maintenance on those parts, keep the systems up for longer. And when you've got something like 20,000 endpoints in a machine, that becomes critical. Of course, there's the orchestration of workload. What we don't want to have is very expensive systems sitting idle, or parts of systems sitting idle, because we haven't done a very clever job of how to schedule work on those systems. So AI optimized scheduling, perhaps based on energy efficiency, on the energy or power usage of applications will be critical. And of course, the number of core components in these systems, 5 million components here, all of which potentially could fail. We have to have the ability to autonomically maintain these systems. So our software, CDC, Cognitive Data Center is the acronym, for predictive maintenance of these capabilities. And then finally, smart management. So the ability to look at the energy consumption of particular applications and optimize around that energy consumption is critical to staying within the power budget that's available. So these are all typically aspects of where AI is built into the machines themselves to drive these next generation platforms. So the new platform that I say we'll be announcing in a month or two at Supercomputing, we can talk separately on particular topics on this, but the system is designed to go from a single rack to exascale size systems. It's designed to embed the next generation and the generation plus one of next generation GPUs and CPUs, so that it will have a lifetime that extends 6 or 7 years to make sure that there's maximum reuse of components. And it's designed to with direct liquid cooling to make sure that all those components are cooled most effectively to drive energy efficiency. And flexibility, the bottom point there. So we work very closely with the major processor and GPU integrators. This platform will have CPUs, GPUs from Intel, NVIDIA, AMD, and also SiPil in the fullness of time, SiPil being the European processor initiative. And that was it. So thank you very much for listening.
Thank you very much. Thank you very much. Collaboration with the office. Thank you very much. So continuing talking about exascale, let's welcome Mr. Smith from the past data. They will be to receive the exascale storage.
Okay, welcome and thanks for having me. My name is Sven. I'm the field CTO of VAST Data. I'm originally coming from the Hpc space. I've been with the German Fraunhofer Center for High Performance Computing for over 10 years, where I invented the BGFS parallel file system. And about 1.5 years ago, I joined VAST Data, where we make a new storage system that's specifically designed for the new era. You know the name of that new era very well already. I think we're very fortunate to not only be here for this new era, but to actually be able to shape this new era of HPC that is artificial intelligence, right? That changes everything. And the decisions that you make and the great ideas that you come up with, they will not only be able to move Saudi Arabia forward, but actually the whole world, right? Change everything for our children and future generations to come. So you probably know very well already that AI changes a lot of things on the computational side, right? Suddenly GPUs have become very important. They were not so important before we had AI. And AI actually also changes everything on the storage side, because now the classic HPC was more about simulation, right? The human had to try to understand a problem, and then that was hard enough. And then even more complicated to come up with an algorithm to simulate a problem or to solve a problem. Very often it's not possible to solve the problem directly, so you have to run many, many simulations in the hope that one of the simulation produces a good result that you can then stay with. This worked for a while, but for the new generation, it became just too complicated, right? For the things that we have in mind, how we want to move humanity forward. So that's why AI is the next level. And AI is all about the computer understanding the problem and then jumping ahead to the conclusion directly. That's the new level. So AI is all about the data. You want the computer to understand the problem correctly and then draw the right conclusion, right? That's why accuracy is so important. You certainly don't want a computer to draw automatic wrong conclusions when you're talking about something like medical treatments or autonomous driving and things like that. That's why data is at the center of this new era. And that's why we felt we have to build a new storage system, specifically not only optimized for the classic HPC workloads, that's also, but specifically also for the new era of AI. What does that mean? That means that the classic pyramid of storage systems that we used to have in the past, that you can see on the left-hand side in gray, just no longer works. In the past, everyone could afford a tiny bit of all-flash storage if they wanted to, but most of the data was locked at the bottom of the pyramid, which I call the archive here, right? Which is typically very large, but very slow storage. That no longer works for AI, because this, what used to be the archive, low-touch archive, is now your main part to train your AI on, right? This is the key value that you have, your data that previously was the archive and that you now need to process again and again. And the AI learns by looking at this data, not only again and again, but also in random order. That's why fast random access to all of your data is now so important in the era of AI. And we all know it probably, random access just doesn't work on spinning disks. That's why we had to build a new storage system that we call universal storage, completely built on all flash. To make that happen, of course, we needed to bring the pricing of all flash systems down very, very significantly so that universities and also the industry can afford all flash systems at very large scale. We made that happen. I won't talk too much here about how we achieved that. We have a booth here actually, so I invite you to join us at our booth downstairs to learn more about this. But the key is it's a new system based on all flash that gives you fast access to all of your data so that you can perfectly train your AI. Skip over that. Okay, so what does this new architecture look like? Because suddenly when your data is the most important thing, right, then you can easily imagine that you have to build very, very large storage systems, and managing complicated storage systems at scale just won't work, especially not at exascale where we are all aiming for, right? So we had to also simplify the management of the storage systems a lot. How did we do that? On the one hand, we came up with this new architecture that is split basically in two sections. In the top line, you see the clients, the compute nodes, your GPU servers, nothing changes for them. We just want to enable fast access to all of the data for your existing GPU systems. So we split the architecture that you can see in black here in two layers. At the bottom, we have the NVMe enclosures. That's where the actual data lives, where the drives are located. And in the middle layer is what I call the protocol servers. This is where the actual file system logic runs. And the very special thing about this architecture is that we connected all of the protocol servers that you have. This is where the clients get the data from, to all of the NVMe enclosures, and with it to all of the data that you have stored in the backend. This is a completely new concept. Even if you build 100 petabyte systems, then all of the protocol servers that run the file system logic are connected to all of the data. That means from a client point of view now, it does not matter anymore which server a client talks to, because any of the servers will be able to give that client the direct reply, because all of the servers have access to all of the data. This is very, very much different from how classic parallel file systems, for instance, have been designed. And we all know that parallel file systems are rather complicated, so we wanted to avoid creating a new parallel file system. And this new model actually allowed us to provide access to the systems through standard protocols that everyone loves for their simplicity and because they make it easy to access all of your data from anywhere. Namely NFS for the Windows world, SMB, NFS for the Linux world, SMB for the Windows world, and even S3 as an object storage protocol that is great for wide area access to the data. All these are just different protocols that access the same data. So you can absolutely say we ingest new data from a medical center to the university via S3. It's a protocol that's optimized for wide area access, or you use S3 to share the data with other universities in the country or even in the world. But for the fast, efficient local processing, you want to use NFS, which is more optimized for local access speed. So that's what the VAST system allows. And that's why it's a universal storage system, because it makes it very easy to access all of your data through many different protocols and from everywhere in the world. But a classic limitation with NFS was the performance. For these GPU servers, they are very data hungry, so it's not good enough to have this classic NFS limitation that a single client can only talk to a single server. That's the main advantage that parallel file systems brought in the past, that a single client can talk to multiple servers in parallel. And now with this special architecture, that's why it's so important, this problem became very easy to solve. Since now all of the NFS servers in this picture have access to all of the data, from the client point of view, they all look exactly the same. The client cannot tell the difference between the various servers that we have in the system. They look like the same single server with just different IP addresses to the client. So that allowed us to introduce a new concept to NFS that we call NFS multipathing. With NFS multipathing, you are now able, instead of specifying a single server IP address, to specify a range of server IP addresses, and then the client will just establish connections to all of these IP addresses and send out different requests in parallel to all of these servers. That's how we close the gap with the simple standard protocols to the performance that you could previously only get from parallel file systems. And at the same time, we put everything on NVMe drives to always give you that maximum performance. And just to give you a quick example of how far this can go, because I know many people have tried NFS in HPC and failed because the classic NFS systems were not really built for speed. So that's something that we changed, of course, in cooperation, among others, with NVIDIA, because NVIDIA is one of the investors in our company, actually. And you probably know the NVIDIA DGX A100 systems, very powerful GPU servers, 8 GPUs, and also 8 200 gigabit network cards in a single compute node here. If you try to read data with the classic NFS approach before VAST data, you were limited to about 2 gigabytes per second, which is not really AI compatible throughput. But we have proven in the lab and at various customer sites that with the new concept of GPU direct storage and the vast enhanced multipathing client, we can fully saturate the network bandwidth of 160 gigabytes per second out of a single NFS client mount point. So that just shows that we have successfully overcome all the previous limitations that you might have known from NFS in the past. I'm running out of time. We also make everything super easy to use. There's a nice web interface. You get automatic alerts. We have a ton of resilience in these systems, all the enterprise features like snapshots, capacity estimations, data reduction, and so on. You can see end to end where the load on a system is coming from, which users or which jobs cause the most load, and things like that. And I want to finish with two customer success stories. One of our larger customers is the Lawrence Livermore National Lab in the United States, which says that VAST for them is really the universal storage, right? Since we solved the problem of AI to make all data always quickly accessible, the system just automatically became great for all other use cases as well. So they use it for their home directories, for their HPC Scratch, and also for their training data. It's the universal storage system that's available to 22 different clusters. And they say that thanks to VAST right now, sharing access to billions of tiny files, the classic hard problem in HPC, is now no longer a problem. And that's the key to their success. And another customer that I like a lot is Duck Down Under Geophysics. They provide a cloud HPC service, everything liquid cooled, as you can see in the nice picture in the back. They come from specifically oil and gas and now are a general HPC service. They say their HPC codes and the codes of their customers now run up to 20 times faster since they replaced their old storage system with VAST. And this is the statement at the top that I like so much. They say VAST hasn't just changed the way we store data, it is changing our relationship with the data. That makes me very proud, right? That we show that thanks to the right storage system, new things become possible. And that's it from me. Thank you very much.
Where high performance computing was utilized, data processing, computational field. This will come in the evaluation you'll be visiting about leveraging high performance computing for big data costs.
Assalamu alaikum. Good afternoon, everyone. My name is Badr Badghish. I am a geophysicist with Saudi Aramco. My presentation is titled Leveraging High Performance Computing for Big Data Processing. This work was done by myself and my colleague Gino Ananos from Saudi Aramco. The outline for this presentation is that we'll go through a short introduction for the data used and the motivation behind our project. We'll later introduce an algorithm and its optimization for high performance computing, and we'll summarize the work in the conclusion section. For the dataset and background, we use reflection seismic data in our project. In short, reflection seismic data is a collection of reflection events and relative to time. Here's an example of the process of acquiring seismic data. In land seismic data, we typically have a source, and this source can be several vibro-sized rocks that check the ground, sending energy pulses that would reflect from different layer interfaces due to various rock properties. And then the reflected energy would be picked up at the surface with a geophone. A geophone would measure or detect the movement of the surface and convert it to electrical signal. So as I said, the source would send energy pulses that would get reflected from the subsurface and picked up by the receiver. And at the end, we will have a seismic trace. And typically, when we do seismic acquisition, we would have multiple receivers assembled in arrays. And these receivers then stack to produce a seismic section. And typically, seismic sections or seismic surveys cover large areas in the forms of 2D. 2D seismic survey is an example of this one. And also, we have 3D seismic volumes where they cover large areas, and they typically cover areas in the magnitude of tens of square kilometers. 3D seismic surveys are in the magnitude of petabytes in size, according to a 2018 paper. The amount of data generated by a single seismic acquisition survey in 2016 was estimated to be 2.2 petabytes in size. The motivation behind our project is that seismic data requires conditioning and processing. Due to the nature of the seismic data, we need to employ advanced image processing and noise attenuation. Also, the constant research and development in our field, geosciences in general, and specifically seismic image processing, requires us to quickly implement and evaluate new ideas and deploy them on HPC resources. So for our test, we use an algorithm called non-local means filtering, or NLM for short. NLM is an algorithm, is a subset of mean filtering. NLM works by taking a pixel and calculating the Euclidean distance from that pixel to other pixels within the within a similarity window, or let's say a batch within the similarity window, and it would then take the weighted average for all the pixels or all the patches within the similarity window. So we fed a noisy seismic section to our algorithm, and for example, this seismic section has a lot of random noise, and we also wanted to preserve thin reflections within the seismic section. These thin seismic reflections can be correlated to subsurface structures. So after feeding the noisy seismic section to our algorithm, we were able to reduce the random noise within the section, and also preserve the thin reflections in the input dataset. Now moving to the algorithm optimization. So some of the challenges that we face in our field, especially in seismic processing, is the development turnaround time. Normally, we need to optimize our algorithms for high performance computing deployment, and that would requires a lot of testing and assessing these algorithms. Also, the testers that take these algorithms and run them on our datasets are concerned about the runtime for these algorithms, and the ease of use for running these algorithms on the test environments. So the normal workflow for algorithm optimization is typically done using C and C++, and optimized for HPC resources using OpenMP and NVIDIA CUDA. This could be a bottleneck for our researchers, since it requires a lot prior knowledge of programming and the knowledge of these optimization frameworks. So one solution could be the use of a simple and easy to use Python programming language like Python. Python is can be easily picked up by our researchers, and when paired with the hardware acceleration libraries like NumPy, it could allow for the utilization of parallel CPUs and GPU computation. NumPy is a just-in-time compiler that translates a subset of the Python code and the NumPy code to a machine code, and this pairing can help our researchers to quickly develop and test their ideas. Now comes the interesting part, the algorithm optimization result. So we wanted to test our NLM algorithm on a single node. So we used a machine with 2 Xeon processors and a single RTX A6000 GPU. The environment was based on Python 3.7. So we tested our algorithm with 3 different data sets. We used a 0.21 gigabyte, 8.8 and 48 gigabyte data set. We fed the first data set to our pure Python implementation and was able to process it in 16 hours. Then we ran the same data set on our CPU optimized algorithm. We were able to achieve 31x speed up, which is roughly 30 minutes. And also we're able to we ran the same, the other 2 data sets through our CPU optimized algorithm, and we got 19 hours. We get them in 19 hours and 101 hours respectively. Not here, we didn't run them in on the pure Python implementation because based on our estimations, they would take from 1 to 4 months to complete. We also optimized our algorithm for GPU computation. We were able to achieve an additional 19x speed up for the first data set. That puts us at 589x speed up when compared to the pure Python implementation. Also, we achieved a 16x speed up for the GPU implementation on the other 2 data sets. Something to note here is that this optimization was achieved with a few lines of code added on top of the already simple Python implementation. In conclusion, image processing is crucial for seismic surveys due to the challenges that we face in the subsurface. Seismic surveys require high performance computing resources due to their massive size. Algorithm development and optimization can be improved by integrating Python in our development workflows. Python libraries allow for GPU and parallel computing, CPU computation. And this work can be easily transferred to any other research field with large datasets. Here are the resources for this project. At the end, I would like to thank the HPC organizing committees, Imam Abdurrahman bin Faisal of the University, and my colleague, Dr. Saleh Al-Dosari, Khalid Garni, and Dr. Muhammad Safi from Saudi Aramco for their support. My name is Wali Batesh, and thank you all for listening.
And now last but not least, welcome Mr. Paul Brook, who will be presenting about data analytics and AI microphone. He will be joining us here soon. Mr. Paul, do you hear?
Hello, hello. I heard my name.
Yes, Mr. Paul, you may start when you're ready. Thank you.
Excellent. Do you want me to share my screen, or has this been uploaded for me?
That's fine.
Share from you. You can share.
Doing that now. Okay. Thank you, everyone. And I profoundly appreciate the privilege of being invited to talk to you about HPC, AI, and data analytics. What I want to share in the short time we have together is the big trends, as we've seen with, very lucky to catch half of the seismic presentation there. We're seeing new paradigms, new ways of working and thinking being fairly rapidly introduced to the HPC community. We're seeing across numerous customers, both in the private sector and the government sector, ways of working that mean the traditional HPC is morphing. It's using elegant and new languages, and Python is something I'm comfortable and familiar with. As that brings in identities that we would wrap around artificial intelligence that a few years ago were very expensive and difficult, are now with huge provisions of libraries from the likes of Google and from NVIDIA, from libraries that are published from the community itself. And then the big familiarity, which is taking the large data sets familiar to the advertisers of this world, the social media, data sets that, as you would hear from Aramco, that at a scale that was unfathomable 10 years ago. But that creates its own problems, and a very busy slide that will be super comfortable to share, nothing private or confidential on this, but findings from our installed HPC users, our AI folks, the folks who are dealing with these large data sets, is that getting the energy into the system is the bigger problem, not getting the data into the system or finding the libraries, finding people who are skilled in things like Python with the PyTorch libraries. Those are now the commodity. The rarity is the energy to power these, as incredibly hungry and thirsty systems keep looking outwards to develop better science, better business outcomes, but inward looking, they're consuming energy at a rate that even the hyperscalers and current data center architectures were not designed to service. So we're seeing that claim of density become a significant issue for every organization. Now we, as Dell Technologies, look at fresh air cooling. We've been building for many years modular data centers that are self-enclosed units. They can run much hotter. And innovations along those lines are going to be significant. If you're taking huge data sets, processing on site, and then distributing to a broader community for reprocessing or post-processing, we will see that CERN type model, we believe, increasing. So you're not having hot spots of energy consumption that are actually then limited to the processing and data production by the energy that is available to them. Interesting prediction, and I am super conscious of the organization and the location, but energy still remains a significant input into the output of artificial intelligence, data analytics at scale, and the high performance compute problems that we saw being solved so perfectly by the seismic team at Aramco. Equally, we are seeing a huge trend towards the HPC consumer saying, I want this as a service. Now, this may be a seismic engineer, maybe an automotive engineer. I'm familiar with an individual in my country, and I'm talking to you from near London, England, who spent his life working with an automotive company, just doing the computational fluid dynamics for the windscreen, so that when you press the button on the windscreen, if you live in a cold country, the windscreen does not shatter because it's cold and you're suddenly injecting energy into the glass. Equally, if you're in a hot country and you press the button, the glass doesn't start to behave in a bad way, becoming either more flexible, dropping out of the epoxy resin, or simply becoming hard to see through because of the energy that's being pumped into the glass when there's energy from sunshine already arriving at that laminate. They're complex material problems being solved, and they are becoming more fine grain all the time. But the individual designing that windscreen and the team they represent is a windscreen. That individual is starting to say, I don't want to build my own set of services. I just want to run the computations. I understand the physics of what I'm trying to do. I understand that I can do this at a granular level. Now let me just pick what it is that I need to do. Let me go pick which AIs are going to predict what environments certain products will go in. That trend is increasing as the user base, the people consuming high performance compute increases. And I found a fantastic example of artificial intelligence deployed on HPC in the energy distribution business, where underneath the power lines, often vegetation grows. Now, you don't necessarily want that vegetation to grow too high. You don't necessarily want that to dry out, become a fire risk. Equally, you don't necessarily want no vegetation at all. There are other risks associated with that, with wear and tear on the land the pylons and towers may be put on. The AI analyzes vegetation and the status of the ground by just flying along and reading what the drones generate. The people who then take the AI recommendation and go and cut down the vegetation or actually plant stuff to retain the surface, they just want to consume the recommendation. They're not interested in seeing the mathematics behind the AI's recommendation engine. The more and more we're seeing that desired outcome being delivered to consumers in a very visual way. And I say consumers because it is our opinion that the as-a-service model for people who develop, design, research, plan, more and more is going to get further and further down the line to a point in the future where HPC as we know it can be visualized as outcomes by people who might not be directly attached to research community, but may fund it or benefit from it. True critical mass will be reached then, and you will find incoming data becomes scaled to the number of people that are viewing or participating in whatever experiment it might be. So it's an interesting area. As we see here, a series of models that will become as a service is going to become what we believe a true as a service proposition, not just for the direct researcher, but for the associated teams around that. And the power of the outcome-based HPC statement will be, we believe, a highly visual, highly interactive outcome that will give you as researchers a feedback loop. Interesting times. Our final trend is possibly a controversial one. Now, quantum computing is one of those areas where I do not have a product that I can pick up and say, this is my quantum computer. I always joke to various salespeople that, yeah, this is a quantum computer, a little red box, there you go. And they all go, really? And I'm like, no, don't be crazy. What do you think this looks like? But the necessity of quantum computing and the reality of the direction we are going means that we are going to see that the disruption it brings and the preparation of quantum simulation become a very major area, not just for the AIs to start predicting that and the algorithms that you generate in Python with your PyTorch libraries. We're going to see the simulation on new and specific silicon, the accelerators that we see from GPUs and FPGA acceleration. And we believe we're going to see the rise of the x86 simulation for quantum computing. So the right sort of breakthroughs will happen, because when a quantum computer becomes commercially viable, it is the software and the outcomes that software generates that is going to be the big thing. Again, we believe the sheer scale of the data that the quantum world of computing will consume will dwarf what we have today. And we're fans of the statement, data is in three states. It's either sitting waiting to be computed, it's being computed, or it's somewhere in between, moving from where it's being held and where it's being computed. Three simple states. But we believe the hybrid model that will come before the full quantum computer is an area where research and the scale of data will be a significant positive towards the development of what will be commercially and research viable quantum computing environments. And that hybrid age is likely to last a while as more and more software development becomes apparent as a simulated event, as well as software developed native to the quantum environment. Now, we've had a very, very short time together, and I really am so delighted to have been able to make the time, and equally so sorry that it was not within my gift to be able to be with you in person today and shake hands and take questions over the coffee and the tea. Maybe next time it will be my privilege to be with you in person. But for now, I hope you've found that the last few minutes, an interesting look at the future, an interesting view of where AI is developing, and what it's limited by is not the coding and not the infrastructure, but by external issues such as the input energy. We've taken a look at the demand for the model of, no, I want to consume a service, and we believe that'll be a highly visual service, highly interactive service, and you will extend that beyond your current customer base, inverted commas, customer base. And we finally believe, as we step into an age where we simulate quantum computing and genuinely start to deliver it, the hybrid nature of what you're familiar with today and what the quantum computing world will bring will probably last longer than you believe it to. And my evidence would be, while many people predicted the end of the mainframe, we still see a good number of them providing productive computational output for the organizations that use them. Quantum will not replace overnight. Quantum will hybrid for many, many years. It will be data-driven, and consumers will demand more and more. With that, I look forward to meeting you at the panel session, and I thank you very much for your attention.
Thank you very much. Provided with us, and looking forward to having you and the third management coming in this summary. So now we reach the end of this session. We will open the floor now for questions and answers by the speakers. So if you have any question, you may submit it yes, no, or in various So I'll start with the question that I have already received. I have a question for Mr. We hear a lot about digital twins. Does high performance computing have anything to talk about digital twins? Yes, Mr. Go. Is it still hear us? Mr. Go. I think we lost the connection.
His microphone is muted.
Okay, so I think your microphone is muted. You can unmute your microphone, please, Mr. Root, and the Bergman as well, so we can have a discussion. Okay, what is okay, so let's shift to the Bergman. Dr. Bergman, in your interesting presentation, you have talked a lot about digital imaging. So, there might be specific challenges that you usually face with imaging, and how you usually overcome this challenge in your work.
I could not hear the question well, please.
Sorry. So in your presentation, you talked a lot about digital images you use. So is there any specific challenges and any methods that you, or any like countermeasures that you usually take to overcome the issues of medical imaging?
So you want me to elaborate on the medical imaging? This is what I understood.
Sure, the challenges you usually face with medical imaging in your work and how you overcome these challenges.
I really
Like in processing the medical images themselves.
Maybe if you can get close to the mic, because I really can't really understand the question. I don't hear it. It's a lot. There are some noise.
Sorry about that. Now, is it clearer now? Yes, Rahman. In your work, you work a lot with, the digital images for diagnosis, for example, X-rays or different images. So is there like specific challenges that you usually face with these images, and how you usually overcome these challenges?
Well, one of the, yes, thank you. One of the problems, of course, is well, in medical imaging, we are treating a lot of images. So the data definitely is a problem. The storage is a problem. And as long also one now let's talk about how to acquire the images. One of the problems to acquire images is to get agreement with hospitals, because those are patient data. So there must be a smooth process to acquire the data. Most of the hospitals have tons and tons of data, but they are bound by legal rules and legal terms that they cannot share this data. Unfortunately, if we don't share the data, we don't learn from the data, and we don't advance in the imaging and treatment. So there are two challenges for me. The first is to get the data from the hospitals. This is a legal problem. And the second is the storage, actually. Of course, we have other problems like the reconstruction, but this is our work, this is the research. We researchers, we need to solve these problems. But mostly it's about the data storage and also accessing those data.
Thank you very much, Dr. Adnan. Another question to Mr. Andy. So Atos is about to launch its new hybrid supercomputer. Can you please tell us a bit more about it?
Can you hear me now? Yeah, thank you. So the new supercomputer is designed to be hybrid. So in principle, it will have the ability to mix CPUs and GPUs from Intel, the NVIDIA, and so on. Because we believe the next generation supercomputers are not going to be a one-size-fits-all approach. They will be hybrid, and they will be tailored to specific needs. So in some cases, it may be you want to mix of more GPUs to run AI workloads and CPUs. The next generation of processors are going to be much more shared memory between the CPUs and the GPUs, much more than today's processors will, which will lead to some programming efficiencies. Those will be accommodated in the new platform as well. But the key differentiator for us comes back to the point I made earlier, and also the point before around energy efficiency. So we use very advanced direct liquid cooling to cool every aspect of the system, even the power supply of the system. I'm using water cooling to extract something like 98% of the heat generated to water, which leads to a very low PUE power utilization efficiency, which ultimately drives down the total cost of ownership of the platforms, reduces the carbon footprint, and reduces the amount of electricity used to run the systems. So we look forward to launching those, and to, if anybody wants more information on exactly how that works, very happy to talk in a bit more detail about that.
Thank you very much, Mr. Andrew, and wish you all the best for launching this. Next question is for Mr. Badr. What's next for seismic data exploration now that the foundation for HPC using CUDA Python was established and reported to us here today? Will the team consider upscaling the efforts using either multiple GPUs linked, or perhaps by deploying using multiple nodes?
Definitely we have the capacity to run our algorithms on multiple GPUs. In fact, we have several processing algorithms running on multiple, not even multiple GPUs, but multiple nodes on clusters. For example, full seismic inversion and other seismic image processing techniques run on these in this fashion. So yeah, for this example, we're using Python. We only run it on a single GPU. It's a limitation with the number library, but definitely can run on multiple nodes using the CPU implementation.
Thank you very much, Mr. Burger. The last question for Mr. Smith. With the announcement of the ADA log-based architecture for GPUs that was made by NVIDIA very recently in the GTC conference, does the company plan on expanding the current infrastructure to incorporate new hardware to scale up the operation for its clients?
Oh, excellent question. Thank you. Yeah, indeed, I enjoyed that keynote recently very much, also because VAST was directly mentioned as a storage solution and as an NVIDIA partner in that announcement. As I told you already, NVIDIA is also one of our investors in the company, so we have a very close relationship with them. What I briefly mentioned in my presentation is that we came up together with NVIDIA with implementing this new concept to move data into the GPUs, which is called GPU direct storage. So previously, the way to get data into the GPU was to read it first into the main memory of the client, and then afterwards you had to copy it over to the GPUs. That was a detour that imposed a severe performance bottleneck. And GPU direct storage now means that the data, if the file system storage supports it, which we do, can flow directly from the network card into the GPU memory. So that's how many of our customers unleash a whole new level of performance for their GPU computing. Fortunately, this concept is completely generic. It does not only work with today's generations of GPUs. It will also, of course, work with the new loveless generation. That's why I think we're very well prepared for that, and will also really support that.
Now we are reaching the end of the first part of session 2. So I would like first to thank all our esteemed speakers for the very interesting, insightful presentation and the information they provided us today. And I would like also to ask the Abdullah to join us on stage to honor our speakers. First, we would like to thank our online speakers who gave us from their time and joined us via Zoom, and we will be sending your certificates online.
Thank you.
Mr. Smith-Brunner. Mr. Badr Baglesh. We'd like also to thank Dr. Adnan Buhari and Mr. Paul Brook for joining us tonight. Thank you very much.
Thank you.
Thank you very much. 2 of session 2. We have with us Ms. Maryam Awad, a senior software engineer of Bright Skies Technologies. She will be presenting about leveraging DAO's storage system for seismic data storage and manipulation. So please join me to welcome Ms. Maryam.
Yeah, you can start now. Okay.
Hello everyone. So today I'll be presenting a project that Bright Skies has been researching in collaboration with Intel to start leveraging the DAO's object storage system for seismic data storage and manipulation. So before going into any details related to the solutions that Bright Skies is actually researching and exploring right now, we have to first of all discuss a little bit about what the DAO is and what does it stands for, and a quick comparison between different object storage solutions. So first of all, let me quickly recap the difference between the object-based storage systems versus file-based storage systems. And mainly what makes object-based storage systems more reliable is that it can easily scale to petabytes and beyond, since object-based storage systems mainly has a flat structures, which offers an ease of access to the data stored in the system, while on the other hand, file-based storage systems also can easily scale and are still reliable, but with a performance cost that's incurred with the increase of the number of the files that are stored in the system itself. Also, this is mainly due to the hierarchical structure of the file-based systems and the way that the operating systems manipulates and manages and handles each file in the system. So moving forward, I would like to compare the DAO storage engine versus other conventional storage engines. First of all, the DAO stands for Distributed Asynchronous Object Storage. And since the object storage is much more reliable and can easily scale, so Intel has designed the distributed asynchronous object storage system from the ground up to be totally built in user space, totally bypassing the operating system, and the communication is totally end-to-end, is done in the user space without interfering with the operating system at all. So, and also it's built from the ground up to utilize the new NVMe technologies that are introduced by Intel, the new Optane SSDs and Optane persistent memories. Also, on the other hand, other conventional storage systems are still reliable, still can still utilize new hardware, but they are mainly designed for rotating storage media, can also still utilize the SSDs, but mainly the communication in conventional storage systems is depending on the block Linux kernel IO layer. Still, this block Linux kernel IO layer is offering many optimizations and tries to aggregate the IO calls and so on that are done by or that are requested by the application itself, but still they are not relevant to the new hardware architectures that are that Intel actually is moving forward to. So from the hardware perspective, Intel is targeting, or the DAO storage engine is mainly built on top of the 3D Optane SSDs, where bulk data is stored on, and on the other hand, the Optane persistent memory mainly deals with the metadata and the low latency IO, and in general the headers and the data that are more frequently accessed and requested by the application itself. So moving forward, before we move to our use case, this DAO storage solution can be easily utilized by many applications that are highly and heavily relying on the different on data sets that are increasing in size, just like AI applications and deep learning applications and so on. And one of the use cases that can easily utilize the Dow storage engine is the seismic processing topic. So before going into what exactly our solution is, let's quickly recap the SegWi file structure. SegWi is mainly a very well-known seismic file format that is used to store seismic data. And as we all know, the seismic data sizes are increasing, which depending on the survey area to be in petabytes or terabytes and so on. So mainly this seismic data, these huge sizes of seismic data are stored in SegWi files. SegWi file, as you can see here, consists mainly of 3 parts, and we are mainly concerned with the last part of the SegWi file, which is responsible for storing the traces data that were acquired in field during the seismic acquisition process, and the metadata or the trace header array that is describing the following trace data. As you can see here, the traces headers and traces data arrays are in interleaving structure. These interleaving structures represents a bottleneck that arises during the processing of the seismic data. Okay, next is what we are actually doing at Bright Skies. So mainly at Bright Skies, we are offering a Dow Seismic Graph API. The Dow Seismic Graph API is totally built on top of the Dow storage model to start utilizing the Dow's capabilities in terms of hardware and the object storage benefits, and also utilizing the graph theory. What we are doing mainly is that we are taking the input SegWi files or the seismic data in general, converting it into a native seismic data format that is represented using a graph. This graph format is then taken, and you can start manipulating the seismic data using whatever operation you would like to. You can start manipulating the headers, accessing the headers, accessing the data, filtering it, whatever operation you would like to do. Okay, so Derek, let's go to the benchmarking results. Okay, so our DSG API, during the benchmarking, we have compared our work against the very well-known Seismic Unix seismic processing package on dataset sizes 100 gigabytes, 1 terabyte, and 10 terabytes. The benchmarking was done on Linux cluster. Of course, the DSG API was run on a DAOS environment, and the Seismic Unix was run on a GBFS environment. And mainly we have 3 main operations that we were exploring deeply in the DSG API. The first operation was the parsing operation. And as you can see here, we are comparing the Seismic Unix parsing operation against the Dow Seismic Graph parsing operation. And as you can see, the Dow Seismic Graph here is almost 7x faster than its equivalent operation in Seismic Unix utilities package. And mainly this is due to the way that the Dow Seismic Graph operates and processes the seismic data in batches, while on Seismic Unix, it deals and processes the traces that are stored in a file, trace by trace and individually, which introduces an overhead during the parsing operation itself. Moving forward is the reading of shots using specific metadata header. And mainly during whatever seismic application, RTM, PSTM, or whatever seismic applications that is run, we would request, or the application would request the reading of the data shot by shot or a gather by gather. And this is a very common operation. And as you can see here, a comparison between reading a single shot using the DSG API and using the Seismic Unix operation. And mainly the DSG API has a consistent time to fetch or to get the requested data from different data set sizes, 100 gigabytes, 1 terabytes, or 10 terabytes. It has a consistent time. While in the case of the Seismic Unix, there is a slowdown that can be easily noticed with the increase of the file size 10x slowdown with the increase of the file size. And if we would dig more into the details of why does seismic Unix is 10x slower than the DSG, is that because seismic Unix mainly to read a specific shot or to load a specific gather from the data set, it has to pass over the whole data set. Even if you are requesting some part of the data that is stored in the beginning of the file, it will neglect all of this and it will pass over the whole file before it returns to the user. And while in the DSG format, we are depending on indexing that was built during the parsing operation. We are building indexes for the data using the headers that are passed along with the data. And these indexes are used later on for easily accessing and retrieving the seismic data. So in comparison between the indexing part that I have just mentioned in DSG, of course, this indexing thing does not exist in seismic Unix. But if we can compare it against the parse SigY functionality in DSG also, it would represent only 30% of the total time that was spent during the parsing functionality or the parsing operation. So you can easily, after parsing the data and having a default FLDR, for example, indexing that is built, you can later on request to start build indexing for the data using a different metadata or using different headers, just like the CDB. In this case, the default indexing was FLDR, and then we requested CDB indexing later on. And this way you can have multiple ways of accessing the same set of seismic data without duplicating the data itself or reading the data arrays at all. You just have to go through the headers that were stored and build some indexes for it to facilitate this accessing thing. Okay, just for sake of time. For our next steps, we actually got some promising results through benchmarking our serial version. We were mainly using one computational nodes in our benchmarking. So these results encourages us to start parallelizing the code and explore more the effect of parallelization. Also to start integrating the DSG API in some seismic processing application, just like the RTM or PSTM or PSDM or something, and to start comparing our DSG performance with more optimized seismic IO libraries, and also to start adding some extra features, just like the data compression to optimize the storage and minimize the IO timings as much as possible. And that's it. Just would like to thank Intel and Lenovo teams for their continuous support, and thank you for listening.
Thank you very much, Ms. Merlin, for the important presentation about process systems and seismic data.
Thank you.
You may have a seat to join the audience.
Yeah, sure.
Thank you very much. So, the next talk will be presented by Dr. Sunday Olateji, an associate professor at Computer Engineering Department at the College of Computer Science and Information Technology. The title is Hybridized Hpc and Sample Machine Learning Towards Making Data Speak More Clearly. A unique paradigm used as panacea for improved research and solutions.
Thank you very much. It's a privilege to have an opportunity to speak to us on the topic that has been announced. I'm with the College of Computer Science and Information Technology, and associate professor of artificial intelligence. It's an opportunity for me to share with you the short topic. I say hybridized HPC and ensemble machine learning towards making data speak more clearly. So, and I say it's a unique paradigms union, a solution of panacea towards improving medical research and solutions. Permit me to start by saying, as we know, we're going to have a couple of talks, the introduction, application of AI ML in medical or healthcare. And then we're going to look at the present challenges of having very well medical data samples. Then the solution being ensemble, try to bring everything together rather than using only one. So because the present practice, as we know, there's a policy in machine learning and its related technology. The principle of let the data speak. So the available data set will determine what information you can gain and what benefit you can actually take from the data set. So it means if the data is noisy, if it has some issues, then the system, no matter how powerful the algorithm you are using, you might not be able to achieve what you want to achieve. So, however, to make the data speak clearly, we need very enriched data. Presently, we start by saying the advent of artificial intelligence over the past few years has definitely revolutionized the way healthcare is being carried out, and a lot of opportunities are opening up, as we know. And of course, fueled by the increased availability of healthcare data sets, so there are a lot of opportunities that need to be made. For example, in those days, we wait for people to complain or have some complaints, and they get to the clinic, and then they diagnose them that they have a particular chronic disease. Unfortunately, they say, oh, we are sorry, it is late stage. Then the question is, why do we need to wait for late stage? With available data set, we can be able to preemptively diagnose people even before the slightest of symptom appears. Now, to do this, there are various areas where data set could be actually collected and used. So either in the diagnosis, the treatment and prognosis, or in drug discoveries and patient management. However, there's a very big challenge when it comes to AI in healthcare. The big challenge is that it's usually, healthcare is usually characterized by huge data sets, complex, distributed, rapidly growing, and foremost of it is we can see different types of data sets. We have the unstructured text, we have medications, we have the lab tests, the one we call the clinical tests, even demographic tests or demographic information, basic information about people. And also we have the imaging, which is getting even more popular these days. However, what we do presently is to pick one of these particular data sets. You see, we pick one of them and then we try to diagnose based on that, or we try to do drug analysis based on that. So the idea is that this is a limitation because it's not possible presently to have clinical data, image data, and also different type of data formats, merge them together, and then to get something that is better for the healthcare. And actually, this is what we need to be able to do. However, with the limitation of the system we have, we only pick one data types and we proceed to analyze, which means a couple of information on knowledge that we are supposed to derive from this might be missing or deficient. Now, so that's why we say towards making data speak more clearly. If you want to take advantage of this, we need to be able to combine so that we don't need to limit access to either the clinical data or the image data. Can't we combine all of them? Data from imaging, clinical, demographic, bring them together. In this sense, as we have presently machine learning as a single model can only deal with only one type as a person. But with ensemble machine learning system, this is what we propose. With an ensemble, which is usually regarded as the machine learning interpretation for the wisdom of the crowd. You need, the idea of ensemble is that you can see when you have very complicated data, no single model can understand the entire data set. So like you can see this set of people, someone is looking at this elephant, one is looking at this, one is saying, okay, it's like a big snake because of the position is analyzed. And this is the nature of data set. Some algorithms are able to see only one side of the data, why other algorithms are good at other side of the data set. So we have this particular kind of system. So based on this, you can have different models, model 1, model 2, model 3, as many as possible. The other side of the elephant also, we have other models. This shows the complications that arise with the kind of data set that are very rich in healthcare that we can use. What happens is ensemble gives the global picture. You see, when you try to combine everything together in what I do call them mushakel, so cocktail, it's like making a cocktail of different machine learning models. So that with this, each of them will say, okay, I can see this, I can see this, and they come together to generate better results than what an individual can ever produce. Now, the idea of ensemble springs from the fact that if somebody goes to the clinic, a doctor will try to diagnose you. Naturally, you want to listen to another opinion of another doctor, especially when they are going to recommend very serious operation or procedure to be done. You want to listen to different opinions and try to come up with the one that is unique among them. This is what we do in our day-to-day activity. We tend to rely more on different opinions of people. Okay, 10 people out of 20 I consulted, 15 of them agree. I think I'm on the safer hand. This is the idea of ensemble. Now, so in a ensemble system, you have different, what we call weak learner. You can read weak learner 1, weak learner 2, and it can go to as many as possible, uncountable. So each of them will model, just like we've seen the elephants, they come up with what they can understand from the data set. Because something unique about machine learning algorithm we need to know is that every algorithm comes with its own hypothesis space. So the hypothesis space will now determine the hypothesis function. It means the more hypothesis space you have, the more the possibility of capturing better information from your data set. Now, so we say, why ensemble? Why do you think ensemble is the appropriate thing to use? We said because when you make choices based on the advice of various people or experts, you tend to get better outcome, and a lot of practical examples have demonstrated this. A popular example we might know is the Netflix competition, when Netflix asked people to come and improve their recommendation system by 10%. People came from different parts of the world to try to come up with the model that can give them the best improvement of just 10%. They couldn't achieve it. No single group could achieve that. The multiple groups now came together before the end of the competition, submitted their different models into an ensemble, and they were able to achieve 10% improvement. So a lot of real-life applications have demonstrated that with the power of ensemble, we can take machine learning to the next level, as the case may be. Now, advantages, there are several advantages of ensembles. So reduce the variance and bias, lessen the impact of cost of dimensionality. As we know, the more the number of features, the more the number of samples we need. However, with an ensemble, you can create individual model with different features from this data. So the problem of cost of dimensionality may not really arise. And also, when you combine multiple independent and diverse decisions, each of which is at least accurate more than random guessing, then errors cancel each other and we're going to arrive at a better result. And there's a mathematical proof for this, that when you have several models trained with diverse characteristics, this is each classifier has an error rate of 0.35, for example. So assume that the classifiers are independent. Independent in the sense that you need to make sure that this classifier has different hypothesis function. So you are recommended to have different algorithms, deep learning, KNN, supercomputing machine, and so many other algorithms. Bring them together. The probability that the ensemble classifier will make a wrong prediction is given by this particular mathematical system that has been established, which is 0.06. We can see that it reduced from 0.35 error to 0.06, which is a very big improvement. And as we're going to see, we have seen practical demonstration of this. We show this one, whereby individual models that are coming together, they were not able to achieve 100%. In fact, we can see this. You can see here, these are 5 machine learning models that have been trained, tested on this system. The first row is showing the correct answer. the actual target we are supposed to get. Model 1, we can see what is predicted. You can see the second model is has made like 3 mistakes. Third one is making also 3 mistakes. And host of other you have mistake and mistake like this. Now, what we did is when we combine them, you can see 57% accuracy, 57, 71. The maximum accuracy there is 71.4. However, when we made the ensemble combination, we arrive at 100% accuracy. So a lot of real-life applications have demonstrated with proper ensemble modeling, we can come up with better results compared, which is not possible for individual models. We also have it, people used to think that linear models are very weak. Yeah. However, when you do linear modeling with ensemble, a simple linear model can actually get you 100% accuracy. We can see these are 3 linear models, carefully developed, and you can see that they were able to successfully separate the negative class from the positive class, and they get 100% accuracy. These are the unique power of ensemble machine learning systems. And then I show the generalized format of ensemble system, which is we can have classifier 1, 2, 3, 4. You can continue to as many as you want. Now, you see, we can have the same or different feature spaces, which means you can use different type of feature spaces for your system development. We also have the base classifier could be different classifier, it could be the same classifiers. And also, during the combination, we could have fixed or train rule classification system, with my preference going for the train rule classification system, which is one of the latest areas in ensemble system. However, as big as this particular opportunity in ensemble is, there's a very big challenge that ensemble is facing. And that is due to bringing multiple models together, the ensemble techniques suffer from computational complexity. And this is where HPC is going to come in now. So this is the meeting point between ensemble and HPC. Take for instance, we will have ensemble of as many models as possible. Let's say D1 is a deep learning model, D2 another CNN model, up to D, T can be as many numbers as you want. When you put this together, definitely a simple system cannot run such set of models. So in which case, what we are proposing, the way forward for this is that we want a situation whereby the way forward is for HPC plus ensemble. Can we bring them together so that the integration of HPC and ensemble will go a long way in resolving these computational complexity challenges of the ensemble system? Because presently, because of the computational challenges ensemble poses, we try to avoid combining many solutions that can assist us. We go for those that are of lesser computational complexity. But if we can make HPC available and readily, the combination of these two is going to go a long way, because we are going to be able to make data speak more clearly without considering the effect of computational complexity on the system. And that is why we can see that at the background, we have the HPC platform, and then on top of it, we superimpose the ensemble learning models. So if you can have a unique combination of the ensemble system and the appropriate HPC platform, that is going to be a unique paradigm that is going to make it easier for us to be able to achieve the best possible and a lot of opportunities in the healthcare delivery using machine learning. And that's why we summarize and opine that HPC plus ensemble machine learning is going to give us making data speak more clearly. That is, the idea of removing some data set will be a thing of the past. We pack everything together, let the system pick whatever data that gives us where we are going and the direction that we're supposed to go as an artificial intelligence implementation. It's a unique paradigm uniting ensemble system and high performance computing, which has been spoken about since the beginning of this conference. It's a panacea to ensure that it's a solution to make sure that improved medical research and solutions are achieved. Thank you very much for listening.
Thank you very much for sharing your interesting work and project discussed. The third talk will be conducted by Mr. Bruno Viforte, the VP Group Business Support, HPC, AI, Quantum, and Atlas. He will take us back to the exascale and we'll be talking about challenges of the exascale and why. Mr. Bruno?
Yeah. So my colleague Bruno, he had a COVID incident in his family, so he's not been able to travel. So he asked me to do it in this place. So I'll be delivering it on his behalf. Should we choose this one? Okay. Okay. Okay, so this follows on nicely from the previous talk and also my talk earlier today on reaching exascale. So we're now going to look at the challenges of exascale and beyond. So I've used an example from weather, again, weather and climate here, but again, it could be medical, it could be many other disciplines. But basically, the demand for HPC is continuing to grow. In this case, we're seeing multiple dimensions. So the resolution of the problems, the resolution of the data set. So this is the spacing, the spatial aspects of it, the complexity of the models themselves. So in this case, building in more physics and chemistry into the weather models. The number of data inputs. So in this case, it's satellites, weather balloons, but it could be medical CT scanners, MRI scanners, genome sequences, etc. And then again, we come across this term ensemble. I'm using ensemble here in a different way to the previous speaker. Here it means running the same job again and again and again with slightly different input parameters, so that you can get a probabilistic output for the problem, rather than using multiple different data sets to get an overall view. However, there's some similarities in that trying to achieve the objective of increasing accuracy in the overall result. So this is an example from weather of why the demand for HPC continues to grow. If we look in what the AI aspects and continue to drive AI, we saw a version of this slide earlier today in Jean-Laurent Philippe's talk, basically looking at the learning models, the parameterized transformation models that are used in natural language processing, and the inflection point that was seen a few years ago, and those are continuing to grow. So now, probably this year we'll see GTP4 as a model with greater than 1 trillion parameters. Trying to manage that, there is no other way to do it other than using HPC. So where does this lead us? Well, we then have, as per the previous speaker's comments as well, we have different communities coming together. You have a data science community who has these massive data issues that they need to address. And then you have a high performance computing community who are coming from a background of complex simulation, who quite often like to use command line interfaces versus specific frameworks that have been developed for AI. So how can we bring these two communities together and achieve the panacea that was mentioned about the benefits, the joint benefits of having HPC and AI workloads combined? So that is what we're trying to do with our framework. We call the framework Think AI, but essentially it is about, just jump back, about bringing together these two communities and to be able to couple simulations with deep learning frameworks. An example where this is happening for real. So this is a machine we're building today in Checkerboard in Italy. The machine will be called Leonardo when it comes on stream in a month or two's time. This machine has something like 14,000 GPUs and will be 10 exaflops, AI exaflops in this case, so FP16 exaflops, or 320 petaflops HPL. In the picture that you see, this is the complex architecture here with the full kind of dragonfly plus network connecting all of the components in the machine. The blue boxes represent chunks of GPUs, the orange boxes regular CPUs, and then there's some mission specific IO represented by the pink spots. But the machine will be used for a combination of HPC and AI workloads built by ourselves with NVIDIA and storage provided by DDN in this case. From a software perspective, the Think AI solution is around how to integrate these two workloads. We have an engine called FastML, which is looking at how we can auto-generate the machine learning models from the data generated by the HPC simulations, use those as surrogate models to build and train the neural network using online feedback loops to improve those models and then improve the original data generation of the simulation. So by using this framework, we're coupling together the HPC and AI and bringing together these two different communities in a kind of unique combined environment that meets the needs, hopefully, of both communities. So what are the challenges and benefits of doing this for real? So here you have two pictures. One is the traditional weather model, and the other is the same model, same simulation using a neural network. For the untrained eye like mine, I can't really spot the difference. Which one is the neural network is the question there. So, you know, the use of ML to replace core computational kernels is showing a lot of promise. The dynamics are working very nicely, and this will continue to grow and develop over the next few years. And as a forecast tool, it's become, you know, very good, and the errors and the error rates are comparable. However, there are, you know, and let me just say, you could again apply this to other areas of science, other domains. So very, very promising, but there are some downsides. And the biggest downside is, you know, losing some understanding of what's happening under the covers, the underlying physics. For too long, you start to miss, you know, to miss that knowledge, to skip that knowledge. And then, you know, knowing how to increase complexity and fit different feature interactions into the model. But a lot of promise there. And so what does all this mean for the design of post-exascale supercomputers, the next generation of machines? Well, certainly, and we've heard it consistently this morning, converged HPC, AI, and data into the machines. I said in the comments earlier, the next generation of machines, there will be no one-size-fits-all approach. The machines will be either tailored to specific customer needs, specific workload needs, or more likely will be built of modules, where we have modules that are highly interconnected and can have specific functions. So in this case, we're showing a picture where we have, you know, regular CPUs, we have GPUs, that's quite common today, but perhaps, you know, in the not too distant future, you will see quantum computing modules plugged in as equivalent to accelerators today. We're also already seeing quantum simulators plugged into regular supercomputers. And before too long, you know, perhaps specialist nodes such as neuromorphic modules for encryption and so on. So this is our view of what the future looks like post-exascale as we drive towards greater computational efficiency, greater environmental efficiency, and the ability to tackle bigger and bigger, more tougher problems. Okay, I think that was my last slide. So again, thank you very much for allowing me to speak with these topics.
Thank you very much, Mr. Andrew, for elaborating on the current and future challenges of TAIL, and we wish Mr. Royal. So our final talk in this session will be conducted by Mr. Mahmoud Al-Hassan, Engineer System Analyst at Saudi Aramco, under the title Leveraging Artificial Intelligence to Optimize Reservoir Simulation
Good afternoon, everyone. My name is Al Hassan, and I'm a Petroleum Engineer System Analyst from Saudi Aramco. And today I'm going to talk about leveraging artificial intelligence to optimize reservoir simulation HPC environment. We have developed several AI algorithms to find optimal compute resources for reservoir simulation. This is our agenda for today. Prior to 2010, the engineers used to manually specify the number of cores to run simulation jobs, which might be an overestimation or underestimation this might cause, wasting resources, reduced utilization efficiency, longer queue wait time, or longer simulation wait time. The need arose to devise a mechanism to estimate the number of cores to guide the engineers in their reasonable selection. In 2010, a mathematical model was approached. A mathematical model was developed, taking into account important simulation reservoir data as model size, reservoir type, reservoir complexity, and number of cells. The model size helped to guide the engineers to have a range selected, of course, so they can run the simulation job. In 2019, we have developed an artificial intelligence. We have developed a machine learning model that works closely with the mathematical approach to find the best number of the compute resources, taking into account many other reservoir simulation parameters such as the memory requirements, runtime, static and dynamic data. In 2021, we have major improvements by utilizing the AI. We have developed an intelligent HPC optimization layer to predict the near optimal number of cores and runtime. There are two key parameters to efficiently utilize our compute resources and optimally run simulation jobs. These are the runtime, how long does a simulation job take, and the number of cores required to run a simulation job. In either situation, using more compute resources would decrease the runtime. However, if we increase the number of compute cores, what we will have is we will increase the communication skills. We will get the communication between the compute resources, which will have scalability of parallel applications. So let's take an example. If we increase here from 1 core to 500 cores, we have improved the run by 90% in this sample case. But if we keep further increasing, we will linearly decrease the runtime. But further increase will result in more. Further increase will result in more, which will result in waste of resources because we're going to use a lot of compute cores. So what we did is we can find from this investigation is that there is a sweet spot between the runtime and the compute cores, which we can have the optimal number. And this is what we're trying to predict prior to running the simulation job. And this will help us to reduce the compute capacity, reduce the runtime, available compute capacity, improve the wait time, and improve HPC utilization. We capitalize on big data and mining and AI to efficiently solve this nonlinear multidimensional optimization problem. So let me explain, starting with data mining. In real time, 24/7, we are collecting necessary data for each simulation model running on the reservoir simulation environment. This includes the model size, reservoir type, reservoir complexity, MPI communication timings, solver convergence and timings, and hardware configuration. And so far, we have collected 100,000 records, and it's increasing on a daily basis. When it comes to selecting the suitable model, we have tested several machine learning models, such as support vector machine, which resulted in 72% prediction accuracy, decision tree with 78% prediction accuracy, random forest tree with 82% prediction accuracy, and deep learning with 88% prediction accuracy. We have selected deep learning due to its higher accuracy and it's suitable for nonlinear problems. In the process, we have created 3 ANN models. The first one is to predict the emission core gas instead of using the mathematical formula, taking into account important key reservoir parameters such as model size, reservoir type, reservoir complexity. After the prediction, we will take it as an input for the second ANN model to predict our runtime. After predicting the runtime, it will be an input for the third ANN model, just to predict the core hours. After predicting the core hours, we will have a near optimal suggested spot by taking the predicted core hours for our next runtime. Now let me share with you our results obtained so far from 4 cases. For the first example, our reservoir simulation model is with 30 million cell size to solve the VDE equations. The y-axis represents the runtime and the x-axis represents the number of cores. We initially started at 100 cores, and we found that the runtime was 8 hours. After that, we increased the number of cores to 500. Which resulted in 1.8 hours. Our mathematical model gave us a range between 1,000 cores and the lower limit is 1,000 cores, the maximum is 2,000. 1,000 cores gave us the 1 hour of time, and the 2,000 cores is 38 minutes runtime. On the other hand, our AI predicted the suggested slot is 1,200, which gave us 52 minutes runtime. For the second example, it's an 80 million cell size model solving the VDE equations. The AI predicted 3,200 cores, which resulted in 6.3 hours. The third model is a 54 million cell size to solve the VDE equations. The AI predicted 2,300 cores, and the runtime was 9 hours. And the fourth model is 12 million cell size, solve the VDE equation. The AI predicted 480 cores, and it resulted in 1.7 hours. So this we can see that after implementing the solution, we can reduce the compute resources, reduce the runtime, maximize memory utilization concurrently, and improve the wait time, avail more compute resources, and improve the efficiency. Since its inception, the intelligent HPC optimization layer contributed to improving the reservoir simulation HPC efficiency and help in accommodating increasing number of simulation runs and other KPIs with runtime and wait. Now I'm going to share with you our deployment results, which has been tested using more than 31 cases. As you can see, the difference between the selected 4 hours and the predicted 4 hours. From this, we have saved around 107,000 compute cores, and the available ones are 14. To conclude, I would like to share with you the benefits and business impact of the intelligent HPC resource optimization layer. First, we managed to significantly improve the organization's KPIs, such as wait time, utilization, and efficiency. We also managed to accommodate more simulation runs on the same hardware capacity. This is an addition for allowing to accommodate several appliances. Thank you for listening.
Thank you very much for interesting experience and achieved results. Very interesting. Thank you very much. So now we are welcoming your questions to the speakers on site or in the room. So if you have got any questions, you can share with us. Yes, I've got some questions. The first question for Dr. Adam. Dr. Adam, in your presentation, you talked about the ensemble model. So will high performance computer contribute to improving the accuracy of ensemble or only reducing its computational complexity?
Thank you very much for the question. Yeah, it's very interesting to know that when we use this new system in collaboration with the Hpc platform, it's not only going to reduce or improve the problem, remove the problem of computational complexity, but it's going to have the possibility of increasing the accuracy and the performance. How? Now, for example, I said let the data speak more clearly. Now, when I just look at one of the presentations of our colleagues, see, support vector machine is noted to be really very powerful, but you can see in this problem, it has lower performance compared to other models. Now, the idea is this: the mistake that support vector machine is making is going to be different from the mistake that ANN is making, and it's going to be different from the mistake that deep learning is making, because deep learning does 88% accuracy. So what ensemble is bringing to the table is this: let's combine the three of this model, all of them. So what we're going to see is the three of them will come up with better accuracy than any of those individual models. So, but the challenge is when you put the three of them together at a go, you're going to have computational complexity. Sometimes we might need to train like one of the very popular solutions in real life was like 135 models. If you have to trace 135 models for a single data with multiple computational complexity, we run into trouble. But if we are able to do that, it's not only that we are going to remove the problem computational complexity, it also gives us better performance, as I showed earlier, that individual model will get 71%, 51%, but when we put the same five models together, we got 100% because of the combination of the system. So it's going to do computational complexity problem resolution and also improving the performance in terms of accuracy, precision, and host of others. Thank you.
Thank you very much, Dr. Adam. The second question is for Ms. Marina. Your previous presentation about the data storage was very interesting. But what key bottlenecks in seismic processing are resolved throughout utilizing something like the data object storage?
In general, maybe before we start so okay. In session we're starting in general before actually the data is used in seismic processing application, just like the RTM and the PSTM and so on. The data passes by multiple pre-processing operations that are targeting actually the noise removal, the sorting of the data, some filtration, some pre-processing operations should be done before the data is used for migration. And mainly these operations, one of the major bottlenecks that are faced during the pre-processing is that most of the seismic processing applications are duplicating the data to apply any kind of sorting or any kind of communication or whatever. So with each post the data passes by, a new version of the data is released, and you can imagine the amount of data that is duplicated. You are talking for a data set that can be megabytes or something like this. So the data set sizes are duplicated. We have many duplicates in memory or in stored in one device, and mainly sometimes only very minor changes are existing in each version of this data. So utilizing the self-hardware along with the object storage that is providing, along with the graph theory that we have utilized using outside graph API, we are offering just one version of the data is stored in memory, and we are just building some indexes for this data, and we are utilizing these indexes during any accessing the data. Also, one of the major features of the data storage system is the version object storage, where if you are having a data set is say for example 1 terabyte of data, and you just would like to change 10 gigabytes of data. You just need to store the changed data bytes. You don't need to restore the whole data set once more. So utilizing this version of object storage along with the graph theory helps in accessing the seismic data and manipulating it faster without burning too much storage in the.
Thank you very much, Ms. This is really very interesting. And the final question is from Salah. So in your model, you presented how many layers of nodes were used in each in letter that help you to achieve the presented results?
Yes, and the first model, in all the models, we have used one input layer and 3 hidden layers in one output layer. For the first model, which is the core model, for the number of nodes, for the input layer, we used 512 input nodes. And then we went to the first hidden layer, which is 256, then 128, and then 64, and then one for the output. The same goes for the one-time ANN model. And for the last model, which is the core hours model, we have used 256 nodes for the input layer and 128 for the all 3 hidden layers and one for the output.
Thank you very much, Ms. And another question for you. What are the features of reservoir data?
The features of the reservoir data, yeah. It's one of the reservoir type, complexity, number of wells, and time maybe and stuff, depending on the problem.
Okay, thank you very much. So now we reached the end of our session for today. So I would like first to thank all the audience and attendees for your participation and your time. A big thank for our speakers who provided us with a very insightful and informative information. So thank you very much all, and I'd like to ask Dr. Abdullah to honor the speakers for this session. So for this, Ms. Marina Mawad.
عشان الإضاءة بس التصوير هذا. ها؟
Dr. Sunday Olatunji.
Yes. Is the question for me? Hello?
أيوة.
I thought there was a question for me.
This is from the previous session?
Zoom.
Okay, so Mr. Bruno Liquanti, on behalf of him, Mr. Andrew will take this. So thank you very much, Mr. Andrew. We hope that you know. Mr. Andrew.
Yes, Assalamu alaikum. Would like to thank all the speakers and all the audience for today for their great contribution and for making the high performance computing a success. So thank you all. Now we'll have our lunch, inshallah, will be the floor. So please join us. Thank you.